on the. Okay, so that's Hertz's experiment. Can you picture that? So it's important that you understand that. Okay, so the knowledge that you need for this type of circuit is just whatever we covered during physics 38. Electromagnetic induction circuits, AC, let's say first circuits, right? Then AC, then DC and AC circuits, and then electromagnetic induction. Electromagnetic induction and Maxwell's equations. Maxwell's equations, which predicts that a changing electric field induces a magnetic field, and Faraday's law that predicts that a changing magnetic field induces an electric field. Right? No, let's see that in real life. I really like this video in YouTube. Let's see in real life how the thing looks like, right? Am I sharing the screen here? You can see the screen, right? It's a YouTube, it's a video.
Yes, yes.
Okay, good. Hertz experiment, right? Here you go. Now take a look here. This guy did this experiment. It's slightly different from Hertz. He's not using two spheres at the end of a rod. He's actually using a conical end here with a little point. Okay, you're gonna see how, but the idea is similar. Okay, so here you go. Here you go. See the sparks? This is spark here. So just something like that Hertz was seeing in his experiment. Okay, he had this guy connected a source and he's generating this spark.
Around 1880, the brilliant scientist James Clerk Maxwell developed the mathematical theory of electromagnetism. His theory predicts that electromagnetic waves.
Okay, this is a different format of Maxwell's equations. This is the differential format of Maxwell's equations. So far, we saw only the integral format. Okay, those integrals that I presented to you can also be written in this differential format as well. Okay, in order to predict the electromagnetic waves, in free space, the charge must be zero and the current must be zero as well. Here's a different format of the electric field. Here's a different format for the magnetic field. Okay, so here goes.
Propagate through the space at the speed of light.
Okay, so here goes. Here's the electric field that's perpendicular to the magnetic field. The magnetic field tags along with the electric field. As the electric field changes, it induces a magnetic field. And as the magnetic field changes, in time, it also induces an electric field. It's a transversal wave. Hertz found out it was a transversal wave. And the propagation of the wave is given by the right-hand rule. But it is the right-hand rule in terms of the electric and magnetic field. It will be E cross B. Okay, keep that in mind. We're going to talk about the Poynting vector very soon, and the Poynting vector states the direction of propagation of the wave. E electric field cross product the magnetic field. So this electromagnetic wave is propagated from the left to the right along the Z direction. The positive Z direction. So that should be X, Y, and Z, right? The X in this case is going to be in the vertical direction.
Many other scientists of the time were trying to prove experimentally the existence of these waves. In 1887, Heinrich Hertz, a German physicist, designed a series of brilliant experiments to demonstrate Maxwell's hypothesis. Heinrich's equipment was simple: a spark generator coupled to an antenna.
Okay, here you go. That's the spark generator. Okay. The transmitter.
and a metallic ring set at some distance.
And that's the receiver, the metallic ring. Okay.
Stands apart. Heinrich proposed that the electromagnetic waves generated at the antenna will travel through space, and if Maxwell's theory was correct, they would induce a current in the ring, and a spark will appear in the ring gap.
Okay, think about that. This guy here is the magnetic field, right? The magnetic field is propagating through space, and this magnetic field is changing in time. If the orientation of the ring is proper, right? You're going to have a magnetic flux through this area. The magnetic flux that changes in time will induce a current in this ring. Okay, it's going to be a current back and forth. Okay, and if the magnetic field changes is strong enough, you're going to have a very high accumulation of positive charges here and negative charges, right? That's going to generate a very intense electric field between those two regions. And if the charge is large enough, you're going to get electric breakdown, dielectric breakdown of the air here in this region. Once you get the dielectric breakdown of the air in this region, the air becomes momentarily a momentary conductor, and you will see the sparks flying from one sphere to the other. Okay, those sparks that are flying from one sphere to the other is exactly the same thing that you observe whenever you're electrically charged and you approach your hand to a metallic object and you have that electric discharge that we all experience in dry weather. So it's exactly the same situation. Okay.
In this video, we make a simplified version of this famous experiment. This project requires a high voltage pulse in order to work, and we will obtain that pulse with a lighter like this.
Yeah, Hertz didn't have something like that at the time, right? But this guy came up with a very simple way of generating a spark. Okay, that's the lighter that we can buy anywhere we want.
One that we have modified for our purposes. Let's open the lighter. Here it is. This is a piezoelectric element that produces a pulse of several thousand volts. There are these two wires that come from the piezoelectric, and we have connected these two wires in order to be able to get the pulse. Here we can see the spark.
Here you go.
Jumping.
See the sparks jumping? Here you go. The accumulation of electric charge is so high there that it causes dielectric breakdown of the air surrounding those two metal alligators, right? That's why you see that spark from one to another. Just before those sparks form, you have a very strong electric field, invisible electric field between those two ends. And then, of course, it's going to have one of the polarities here is going to be positive, the other is going to be negative. And sometimes this one is going to be positive and the other is negative. Now he's going, here you go. Here is your circuit, right? Your spark generator. He came up with those two rods. Note, see the tip of the rod. It's a conical tip. It's better than Hertz experiment because you have a higher accumulation of electric charges here that produce a much higher electric field between those 2 points, right? So I think what he did here is better than Hertz himself did. So that's the transmitter. Okay, that's the transmitter. And what you see in the other end is the receiver. He didn't use a ring like Hertz used, okay? He didn't use a ring like Hertz used, but it works also in the same way.
This is all set up to replicate Hertz's experiment. We have The spark generator.
Yeah, the spark generator is the high voltage source.
Connected to these two wires, and the electromagnetic waves will travel through the receiving antenna. Here we have a neon lamp connected to the antenna.
Okay, so Hertz didn't use a neon lamp, right? But with today's technology, we can do better than Hertz, right? So what he did, he connected a light bulb right in here. So instead of seeing sparks flying from one end to the other, he's just gonna see this light bulb turning on and off. Okay.
And when the spark is produced here, the neon lamp will glow. Okay, I will pull the trigger to generate the spark.
There you go. We can hardly see any sparks here, right? But we can see the light flashing. We can see the light flashing here.
We can see the
okay, now we can see the sparks. Sometimes we see the spark, sometimes we don't see the spark here. There you go. Here you go, here's the light. Okay, here you go. Sparks.
We will now try a more powerful arrangement. We are using now a high voltage power supply. You can build this power supply following the link to the...
No, he's gonna increase the juice to the whole thing, okay? And now that's gonna be interesting. That's when the experiment becomes interesting.
Video that is now on the screen. This power supply outputs several thousand volts. The output of the power supply is connected to this capacitor. The capacitor stores...
Remember that circuit of Hertz also had a capacitor? So here you go. He included a capacitor in his contraption as well.
The energy and the spark will be more powerful in our transmitting antenna.
All right, look at that. Look at the spark here. And take a look at the neon lamp. Okay. So this is the electromagnetic waves propagated from the transmitting antenna to the receiving antenna and lighting up the light bulb. That's how Hertz did his experiment, and that's how he revolutionized the whole
around 18
society. Okay, the idea, the story goes that, remember, this experiment was revolutionary. Okay, and yet Hertz himself couldn't see the importance of this experiment himself. He couldn't see it. Okay, here you go. Hertz did not realize the practical importance of his radio wave experiments. He stated that it is of no use whatsoever. Okay, it's no use whatsoever. Hey, folks, what we use today as cell phones is based on those Hertz experiments. This is just an experiment that proved Maestro Maxwell was right. That's it. That's what Hertz himself thought of his experiment, right? We just have these mysterious electromagnetic waves that we cannot see with the naked eye, but they are there. Asked about the application of his discoveries, Hertz replied, nothing, I guess. Well, the application of his discoveries was that today we have wireless communication through cell phones, first with telegraph, right? First they did that with telegraphs, and then nowadays we can do that with cell phones, and we can even communicate with spaceships that are spacecraft that are far away, they're at the edge of the solar system. Okay, Hertz proved the existence of airborne electromagnetic wave led to an explosion of experimentation with this new form of electromagnetic radiation, which at the time was called Hertzian waves. Hertzian waves. And then until 1910, they start to call it radio waves. But then 10 years, within 10 years, researchers like Oliver Lodge, Ferdinand Brown, and here you go, Guglielmo Marconi, the Italian guy, this guy that became famous and very rich, employed radio waves in the first wireless telegraphy radio communication system. And that was 10 years after, within 10 years after Hertz demonstration, right? And then what happened? Brown and Marconi won the Nobel Prize in Physics, okay? I would say Hertz deserved the Nobel Prize in Physics because he was the first one who demonstrated that. And the series of experiments that Hertz did was just amazing, Here's the guy that's experimenting with the direction of the electric and magnetic field. That's what Hertz was doing at the time. He was experimenting with the best way of increasing the size of that spark, and he was using UV light to do that. That's when he discovered the photoelectric effect. Okay. Today, radio is an essential technology in global communication, telecommunication networks, and the communication media used by modern wireless devices. So Hertz himself couldn't see the importance of his experiment. Apparently that's because he didn't have much of a commercial view, the commercial implications of his device. But he did other contributions, cathode rays, and the photoelectric effect here, okay? Which was later explained. He discovered the photoelectric effect when he knows that a charged object loses its charge more readily when illuminated by ultraviolet radiation. And he did that while performing his experiments on electromagnetic waves. He made observations in the photoelectric effect and of the production and reception of electromagnetic waves, published in this journal. His receiver consists of a coil with a spark gap. Just the spark gap is exactly what you saw in the experiment, whereby a spark would be seen upon detection of electromagnetic waves. He placed the apparatus in a darkened box. Why did he put in a darkened box? To see the spark better, right? If there is so much light around, you might not be able to see the sparks. You observed that the maximum spark length was reduced when it was. You observed that the maximum spark length was reduced when in the box. What does it mean with maximum spark length? Well, it's the distance, right? The distance between the two spheres there in his device. A glass panel placed between the source of electromagnetic wave and the receiver absorbed UV that assisted the electrons in jumping across the gap. Okay, so today we know that UV is absorbed by glass. Okay, but he tried different types of glass. When he removed the spark length would increase, right? You observe no decrease in spark length when he substitute quartz for glass. As quartz does not absorb UV radiation. Quartz is a different type of glass, right? That doesn't absorb UV radiation. Hertz concluded his month of investigation, reported results obtained. He did not further pursue investigation on this effect, nor did he make any attempt explaining how the observed phenomenon was brought about. It was up to Einstein himself to explain the photoelectric effect. It requires some sort of advanced physics that advanced knowledge that Hertz didn't have. Okay, contact mechanics, this is other contributions, okay? Third Reich treatment, Hertz family converts from Judaism to Lutheranism 2 decades before his birth. His legacy ran afoul of the Nazi government in 1930s, a regime that classified people by race instead of religious affiliation. So, yeah, Hitler's, the sense of Nazis to power affected Hertz's family. Okay, and even Einstein as well, right? Einstein had to leave Germany because of the persecution by the Nazi. Here you go, his family was also persecuted for their non-Aryan status. Okay, legacy and donor, blah, 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 here you go. So that's, there are other nice videos out there. I found another interesting video that I cannot find right now, but if you have time, try to look for videos of this type in addition to this one that you see. There is another nice video that I located in there in which the professor that did the video shows the polarization of the wave by just putting a light source at different orientations next to the transmitter, okay? So that's what we have here. Okay, later on, right? Guillermo Marconi. Guillermo Marconi won the Nobel Prize for his experiments. So we are talking about, last time we were talking about the electromagnetic waves, okay? So here go the equation that we were deriving. So here goes. We have this relationship for the momentum of electromagnetic wave, relation obtained by Einstein, with his theory of relativity. Okay, momentum of an electromagnetic wave, We can also say momentum of a photon. U that you see in there is the energy. Okay, I didn't put E here because I didn't want to mix that up with E for the electric field. Remember that if you have 100% reflective surface, using a 100% reflective surface, the change of momentum of an electromagnetic wave, of the change of momentum of a photon, is going to be something like that, minus 2px, right? Twice is P incident and P reflected. P final minus P initial is going to be equal to minus 2P, okay? And the force that the photon feels is going to be delta P over delta T, right? Okay. For 100% reflective surface, it's going to be something like that. The negative sign is just the direction of the force. So in this case, we are assuming that the final direction of the final momentum is the negative x direction. Okay. So that's what we have here. But there's more. There's more we can do here. Delta P can also be rewritten in terms of this equation right here. Can also be written in terms of delta U, right? Delta U over C. Here you go. Delta U over C. And now what you see right here, now let's use just the magnitude so you don't worry about the direction, right? So we can keep this guy here positive, something like that. What is delta U over delta T? Okay, delta U over delta T is the power, right? Is the power of the photon. Okay, energy per time, right? And now we go back to that equation on pressure that you have learned before. Here you go. I'm going to write that down, the equation for the pressure. The definition of pressure, the very definition of pressure. So radiation pressure now is going to be given. Oh, wait a minute. We have to. Yeah, I'm going to put it power. I'm going to write down power here so we don't mix up with pressure, right? You don't mix that up with pressure. So here you go. It's going to be okay. This power divided by area. Rate of energy through a unit of area. That's what the rate of energy flow per unit of area. That's what we get for the pressure. So if you know what's the power of the electromagnetic wave, you can calculate its pressure. That's the so-called radiation pressure. Okay, this ratio here, we know what this ratio is. Okay. There is a quantity that was invented by a guy called John Henry Poynting. Okay. He came up with an important relation that transcribes exactly what you have right here. Okay, John Henry Poynting. Okay, John Henry Poynting. Define an important vector used even today in electromagnetism. The so-called Poynting vector. Okay, so let's see how this Poynting vector looks like. It is, we call it S. Remember this vector. And it's given by what? It's given by 1 divided by mu naught. Okay. E, electric field. Let's see if I can do that cross. No. Okay, I gotta. There's a keystroke for that. It's much easier if you memorize, much quicker if you memorize that. But at this moment, I don't remember. What's the keystroke for this one? Let's see. Oh, here you go, right here. Here you go, E cross B. Can you remember that? Right? If you do the dimensional analysis of this quantity, okay, you find that the dimension of this Poynting vector is going to be exactly, the watts per unit of area. Okay. Power divided by area. And that's exactly what you have right in here. Power divided by area. Okay, if you go ahead and substitute oh, by the way, because because E and B of an electromagnetic wave in free space are perpendicular to each other, right? The S can be simplified as EB. And by the way, here go. As the Poynting vector, by the way, the Poynting vector indicates the direction of the flow of energy of the wave, okay? Remember I told you that direction, not just the direction of flow of energy, but the direction of propagation of the wave, E cross B. And that's what you end up having here. Okay. Don't forget that electric and magnetic fields are a function of time, right? I'm gonna put it here, not just a function of time, but a function of position as well. If the electric and magnetic field are a function of time, so is the Poynting vector. That's the instantaneous Poynting vector. Don't forget that there is a relationship between E and B, right? What's the relationship? We derived that. We derived the relationship between E and B. Let me see that. B is equal to what? E divided by C. Right? Substituting that here, we get this relationship here. Now I'm going to eliminate the X. No, I'll keep it for now. Like that. Note see that the power per unit of area is directly proportional to the square of the electric field. Okay. Well, we can go a step further here in this equation, right? Because we know that C is what? C is the square root of epsilon naught times mu, mu naught. Here you go. That's another, oh, that's like that. Take out this guy and this relation becomes like that. Oh gosh, no. This one, I want this one here. That's another way of writing the Poynting vector. Like that. But that's something that changes as time goes by, right? Well, there is another quantity. Okay, there is another quantity. There is another quantity that we define called the intensity. an electromagnetic wave, of a wave, not just electromagnetic wave, the intensity of a wave. Okay. The intensity of a wave is defined as, we go EI, as the average over time, as the, here you go, now I can time average of the Poynting vector. We get this Poynting vector, integrate over time, over a period, okay, over the period of the wave and divided by the period. And that was the average is all about, okay? So it's like an integral here, dt, divided by the period of the wave. The integral varies from z to the period of the wave. Okay. When we take the average over the period, we get the maximum amplitude, like we did before. Oh gosh, I hate that. Because the maximum amplitude of the electric field is squared. Okay. We still have let's see, there's more to it. It's not just the maximum amplitude, it's is the maximum. There's still a factor here. We did that in the classroom, right? Square root of 2, okay? Something like that. And by the way, this ratio that you see here is the square of the root mean square of the electric field. Okay. Don't forget the intensity has units of power, watts per meter square. Okay, so we have those relations that relates that's related to the energy of the wave. All right, so we derived the energy density. Okay, we derived the following: the energy density of the wave. We did that, and now the intensity of the wave. Okay, so that's what we have for this part of the course. Any questions about that? If we can do it. Let's say it's 50 right now. By the way, you know, I started correcting the first lab report. Didn't finish, but you'll be getting the correction very soon. Okay, didn't finish, but you'll be getting the correction very soon. Okay. Today let's take a look at the schedule of classes, right? We're still doing chapter, here you go, today is the 27th, we're still doing chapter 33, E&M waves, E&M waves, let's put, and I'm planning a second level on standing waves as well. Why do I have, good, better. That's when geometrical optics start. And I also posted all the homework already posted. All the homework in Wiley Plus for the rest of the semester. Make sure you can access it. We're gonna have a second exam, right? This week on Thursday. Chapter, chapter 17, right? Whatever was left out of chapter 17, and at least 33. Maybe we're gonna get 34 as well. Hopefully we have enough time to do that. There are just a few sections of 17. Remember, part of 17. I documented right in here. I'll keep you posted what's gonna be the exact chapters, but definitely chapter 33 on electromagnetic waves. Okay, exam 1, exam 2, exam 2, exam 2 include the remaining of chapter 17. Exam 2. Skip 17-6, chapter 33, and maybe chapter 34. I'll let you know in advance. Don't forget that we'll ask some questions about the experiment too, right? So here you go, exam 1, right? So you should expect questions about the physical pendulum and the standing wave. Questions about lab 2, 3, and 4. Okay? So study, what you did there, what we cover, lab 3 and 4, and I'm thinking about 2 or 3 questions. Or 3 questions about those labs. That's the material for exam 2. Material for exam 2. Chapter 17. Chapter 33. 8:56. Now let's take attendance. Any questions about that? There was there is a little mistake there in the first exam. There was a little mistake in 2 questions, okay, of exam B and exam A, which I picked it up. I'm going to I'm gonna make up for those two questions that you didn't have all the information in there. It was a total of 23 questions. So because there were two questions that are missing, there's missing information in there, I just would take the average based on 21 questions for the exam 1B, okay? So you don't have to worry about that for exam 1B. For the first exam, for exam 1B, there were two questions that did not have enough information there. I usually don't make those mistakes, okay? But that exam I was preparing late in the night and I ended up, skipping it. Exam 1B. One question had a missing illustration, and the other question did not have the value of the K constant. So what I'm going to do, I'm going to eliminate these two questions from the calculation of the exam grade. Some of you picked that up, right? What about exam 1A? Exam 1A, there was no problem like that, but there was a different type of problem. One of the questions did not have the proper answer. I already corrected that. So if you got the right answer and the exam told that you didn't, right? I will fix that in your grade. So it is possible that you got the right answer, but the exam accused that you missed the question. I encourage you to, warn me about those things, because sometimes it doesn't happen, In general, my exam is like 100% correct, but every now and then we miss something like that. Okay, so in this question, the right answer was as far as I remember, the right answer was 99.9%, right? But which one? I don't remember the question number, Claire, but it was two different questions, okay? I don't eliminate it from both A and B. No, just B. Okay, the mistake was just this mistake here just pertained to B. So I'm not going to remove from A and B, just from B. Okay, regarding this one, there's no need to remove the question because all I have to do is to correct the answer, right? The right answer was supposed to be 99.9%, but the exam, I stated that, how do you call? It was 99%, okay? So, yeah, I believe, I don't remember the question numbers, but I believe it was one of the last in there, but I cannot tell you for sure, okay? Yeah. So one of them was obvious because the question made explicit reference to an illustration which was not there. Okay. Another one, we had the K constant missing there. So let's take attendance now. Any more questions? Let's take row here. Go, Toby, are you there? Toby, I don't see Toby here. Harun, are you there? I don't see Harun either. What about Musa? Musa, nope, not here. Zachary?
I'm here. Good morning, Professor. How are you doing?
Okay, nice. How are you doing? Thank you.
Doing good.
Elena? Yeah, good. Crystal? Crystal, are you there, Crystal? No, Crystal. Let's hide it. Brian Spino. Brian's coming, right? Brian Spino. Robert Faust. Good, thank you. Pedro Flores. Pedro. Good. Lawrence Flores. Just
Yeah, I'm here, Prof.
Okay. Daniel Freire.
Here.
Okay. Next, Amalia Gale.
Here, Professor.
Thank you. Tiffany Wang. Next is Olivia Kruger. Next is Daniel Liang. Sarina Lobana. Sarina is here, right? Hi, Sarina. Looks like she's away from the computer. I'll put a star here. Anthony Lopez. Anthony, I see Anthony there as well in the list. Okay, I'm gonna put a star here. Chuck Lu. Good. David Maes. Ryan McNeil. Alexis Nigret. Alexis, good. Daniel Nwabo. Daniel. Okay, next is gonna be Dave. Dave is here. Thank you, Dave. Claire. Good. Jennifer Ramirez. Noah Raymond. Noah.
Here, Professor.
Okay, thank you, Noah. George Risk. Are you there, George?
Here, Professor.
Okay. Shah. Good. Natalie Santiago.
Here.
Nathan Silva. Darnis Simon. Good, thank you. Kenny Villagomez.
I'm here, Professor.
Thank you. Nolan Williams. Nolan. Hang in there. Nola is not answering. Let's see, I'm gonna put a star here, but Meng is here. What about Olivia? Is Olivia there? Yeah, what a shame. Olivia tried to add to the course. She couldn't add. You know, I don't know why. So looks like the college is having some problems adding some of you. Olivia. So he code 26 should be 29. 26, 29. Okay, any questions before you go for a break? Our break is 9:06 now. Break till 9:21 a.m. Let's take the little break and stretch a little bit and come back in 15 minutes. Okay, see you then. Okay, here you go. I found the video I was looking for. So let me show that to you because it's really nice video on electromagnetic waves also. It shows some more details that the other video doesn't show. Let me start sharing the screen here with you. Here you go. This one. Radio wave properties, ENB dipole antenna. Okay, so we go. Let's see one thing here. Yeah, here you go.
Here I have a 300 megahertz oscillator and a 100 watt.
Okay, oscillator. Here should be the RLC circuit. Okay, so that would be the AC source.
Radio frequency amplifier. Going to be
In addition to the source, there's also an amplifier here. Hertz didn't have those devices at the time, but today we have them.
amplifying the output of our 300.
Okay, well, can you hear the sound, by the way? It seems that a little bit low. Let me get this volume up here. Okay,
Megahertz oscillator and sending it to this dipole antenna.
okay. So that's the dipole antenna. That's the job of the spark gap that Hertz had. Okay, the spark gap is something that was used a lot at that time, and then they started finding different ways of generating electromagnetic waves, and little by little the spark gaps start to be phased out of use. Nowadays, the spark gap is used only in the ignition of your car.
To transmit radio waves. Let's turn it on and see what effect it has on this
Okay.
8 watt.
Right now, he turned on the antenna, the device, the circuit, but you cannot see anything because those waves are invisible. But there is a way to make it visible to the human eye. So he's gonna get this fluorescent lamp.
1 foot fluorescent light bulb.
And look what's gonna happen. Go. At this very moment, there is electric and magnetic field surrounding this antenna. We cannot see it, but there is a way to detect their existence. One of the ways is by using this fluorescent lamp.
If I bring the fluorescent light bulb near the end of the transmitting antenna,
There you go.
it lights up.
There is no power source here. This antenna is not connected to any battery whatsoever. It's not connected to any, they're physically connected to the AC source, right? But it's only being powered in a wireless fashion.
Even though it nor I is plugged into anything. If
It's
I
not
slide
even
along
touching
length
the
of dipole
antenna.
antenna, we notice that the
Here you go.
intensity decreases and is a minimum at the middle of the dipole antenna, and then increases in intensity.
Do you see what's happening here? This antenna was designed so it has a maximum. This antenna was designed in such a way so we have a standing electromagnetic wave right here with maximum amplitudes here, a node right here in the middle, and a maximum right in here. Hertz, when he was performing his experiments, he was doing that as well. He was generating standing electromagnetic waves in his lab. He used a reflective zinc surface to generate a standing electromagnetic wave in his lab. Imagine about that. You're doing that for the first time, observing that for the first time, generating a standing electromagnetic wave. And he did that by using zinc plates that would reflect the electromagnetic wave. So when, and he was using his ring to find out the maximum amplitude of the wave, right? Not the lamp, but the ring, that circular ring. And he could see more or less spark jumping out of that ring. So, and he could find out where the nodes of the electromagnetic wave was. He could find out, Hertz himself could find out where the maximum amplitude of the electromagnetic wave was as well. Once, you know, step by step, right? Once you determine the, let me see here. Once Hertz himself found out where the nodes were located, where the maximum amplitude of the wave was located, then he could determine the wavelengths of the electromagnetic wave, that invisible entity, right, that you couldn't see. And once he finds out what the wavelengths of the electromagnetic wave was, he also had the frequency of the electromagnetic wave, step by step, right? The frequency was given by that switch that you saw. He could adjust the frequency of the switch in which it opened and closed, right? Those mechanical switches that you saw in there. Now, if you measure the wavelengths, if you know the frequency, now you can find out the speed of the wave. And when he did those experiments, he calculated the speed to be approximately 300,000 kilometers per second, which validated Maxwell's calculations as well. Okay, and that was another way of measuring the speed of the light. So the speed of the light had been measured before through other means, by astronomical means, before Hertz himself. Astronomers was observing the moons of Jupiter, you know, and they noted that during the year, the time of the eclipses of the moon, of the Jupiter's moons, varied. It didn't match their prediction. And so they figured out that this time lag between one moment in the year and another moment had to do with the finite speed of the light. Okay? And all those measurements, and they found out a speed of the light that was pretty close to that of today, that we know. And all those measurements were was validated, confirmed, right, by other techniques, like the one that Maxwell used, 1 divided by square root epsilon naught mu naught, and then the experiment by Hertz himself. Okay, so let's continue here.
Again, as I go towards the outer edge of the other side. It's been dim once again.
Here you go.
I go toward the middle.
Here you go. That's the node of the electromagnetic wave. The light bulb is not touching the antenna.
And maximum on the ends.
Here you go. And that's the crest of the electromagnetic, of the standing electromagnetic wave.
So this is evidence that there's standing waves that are set up on our dipole antenna with a maximum in potential or antinodes at the ends and a minimum in potential or a node in the middle.
Here you go. It's a really nice demonstration of this guy is doing here. Right?
We can see a similar effect if I take a simple receiving piece of copper pipe as a receiving antenna, 48 centimeters long. And if I hold it in the middle and bring the fluorescent bulb toward the end, it lights up, even though it is not plugged into anything. And as I move the fluorescent bulb along the length, the amplitude is dimmest at the middle and maximum at the ends.
Okay, so not only we have an antenna here, but this copper bar, this copper tube can also be used as an antenna.
As we saw for the transmitting antenna. Recognizing that the current is.
Do you remember the experiment, the video that you saw previously? The guy put a neon lamp. Now this guy is using another lamp as well, right? Here's the copper tube.
The maximum in the middle of our antenna we're going to switch to one that has a single light bulb and use its brightness.
Okay. Oh, wait a minute. I'm sorry.
It's going to be
I made a mistake here. Oh, let's play from the beginning without interruption, right? Here you go. Staring Daniel.
Here I have a 300 megahertz oscillator and a 100 watt radio frequency amplifier. It's going to be amplifying the output of our 300 megahertz oscillator and sending it to this dipole antenna to transmit radio waves. Let's turn it on and see what effect it has on this 8 watt, 1 foot fluorescent light bulb.
Here you go.
If I bring the fluorescent light bulb near the end of the transmitting antenna, it lights up, even though it nor I is plugged into anything. If I slide it along the length of the dipole antenna, we notice that the intensity decreases and is a minimum at the middle of the dipole antenna, and then increases in intensity again as I go towards the outer edge of the other side. It's then dim once again, once I go toward the middle, and maximum on the ends. So this is evidence that there's standing waves that are set up on our dipole antenna with a maximum in potential or antinodes at the ends and a minimum in potential or a node in the middle. We can see a similar effect if I take a simple receiving piece of copper pipe as a receiving antenna. It's about 48 centimeters long. And if I hold it in the middle and bring the fluorescent bulb toward the end, it lights up, even though it is not plugged into anything. And as I move the fluorescent bulb along the length, the amplitude is dimmest at the middle and maximum at the ends. As we saw for the transmitting antenna. Recognizing that the current is the maximum in the middle of our antenna, we're going to switch to one that has a single light bulb and use its.
Oh, pay attention to what he said. He said that the current is a maximum at the middle of the antenna, okay? Even though the current is a maximum, the electric field here is going to be a minimum. It's going to be a node of the electric and magnetic field, but the current is still a maximum, okay? Sounds like counterintuitive, but that's exactly what happens. The current is a maximum here at the middle, but the current is going to be 0 at the ends of this antenna, okay? Where the electric field is going to be maximum.
Brightness as a measure of intensity. As I move the receiving antenna closer to the transmitting antenna,
look what happens. You're getting closer and closer to the transmitting antenna, and the light bulb gets brighter and brighter because the electric field becomes stronger, right? The closer you are to a source, the stronger the electric field is.
The amplitude gets progressively stronger. We can also see that if I rotate the antenna
There you go.
relative to the orientation.
Look here. Did you see what happened here? Now, you know, those electric fields, they are oscillating along the horizontal direction, okay? When this antenna is parallel to the electric field, it induces a current in the antenna, okay? Now, if he rotates this receiving antenna, there won't be any induced current in the copper antenna. That's what's happening.
We can also see that if I rotate the antenna relative to the orientation of the transmitting antenna, its intensity is 0 when the receiving antenna is perpendicular to the transmitting antenna, and maximum when it is parallel.
That's the type of experiment that Hertz did as well at the time, right? He oriented his ring, his receiving ring at different angles, and he noted that there was some polarization in the electromagnetic field.
We can also see that if I rotate the antenna or align the antenna along the axis of the receiving antenna, that the strength goes down. And if I rotate it so that it is perpendicular to the axis of the antenna, its intensity is 0.
Yeah, again, the electric field is in this direction. It's polarized in this direction. Electric fields are oscillating back and forth in this direction, not perpendicular to the plane of the TV, right? That's why the light is no longer on.
Lastly, if we look at the intensity of the antenna or the receiving antenna as I move in a cylinder
Here you go.
around the transmitting antenna at a constant distance, we can see that the intensity stays constant. These help us visualize the radiation pattern off of the transmitting antenna. Here we have a different kind of antenna from the one that we saw earlier. Formerly, that long, straight conducting antenna was a dipole antenna that was sensitive to the electric field. This is a B field antenna that is sensitive to the.
So what you saw before was an electric dipole antenna, receiving antenna, electric dipole receiving antenna. What you have here is the case that Hertz used, right? He used a magnetic dipole antenna in which you have the currents bouncing back and forth. Here's the gap, right? The gap that Hertz himself used, but he didn't use those two plates. He used the two spheres, okay? And look at the orientation. In this case, the light bulb is maximum because we have magnetic fields perpendicular to this plane right in here. And it's lighting up your light bulb very brightly.
Magnetic field. It has a loop to have currents induced within it, and a light bulb that is connected across a portion of the loop, and also two parallel plates that act as a tiny capacitor, which we can tune using this ruler to adjust the spacing between them. Let's take a look at the luminosity of our detector in several different orientations. We can see that with the loop parallel to the plane of the antenna, it has a high brightness, whereas if I rotate it by 90 degrees
Here you
this
go.
way,
Now the magnetic flux through this circuit is 0 because, you know, basically the magnetic field is perpendicular, right? There is no magnetic flux through this loop here. That's why there is no, the light is off.
it has a minimum brightness. And if I rotate it by 90 degrees once again,
Here you go.
it also has a smaller brightness as compared to the original orientation. This tells us that the B field is maximum in this direction, that it is parallel to the normal of the plane of our of the B field loop antenna.
Okay, so that's cancel it. Good. So I like this video, and keep that in mind. You know, there are lots of good videos out there. YouTube, it's a matter of, you know, do some search, and very good quality videos you can look for. Now let me see. Someone was asking when the exam is, right? So here's only the first exam was on Wednesday, okay? Only the first exam. From now on, the exam is going to be on Thursday. Exam 2 on Thursday, exam 3 on Thursday, and the final exam on Thursday. Okay, so the first exam was an exception because, you know, we had more than 1 week. I just want to give you some time to adjust, right? But then we cannot, but after that, we have to go on with the course. Right now, let me see. Harun is here, right? And Musa is also here. Let me see if I missed anything else. Okay, so Sarina is here. Nolan, are you there, Nolan? Nolan is listed here, but he's not answering. Next is going to be, let's see here, Nolan. Okay, good. Nolan is here. Who else is here? Anthony Lopez, are you here? Okay. And then we have Musa and Harun. Musa, okay, Musa, good. Anybody else? 31 students. Okay, some of the students are left, right? That's disappointing. So that's what we have for electromagnetic waves. We can start moving forward now. Let me get my notes here. So here we go. We are done with electromagnetic waves, and the way I organized here is different from the way it is in your book. In this book, they mixed up electromagnetic waves with principles of optics. It's very unusual how Resnick did that. They put electromagnetic waves in the same chapter as principles of optics, grammatical optics. Let's see here. Energy transport, radiation pressure. Okay, good. So what the book does, you start with polarization, right? We usually leave polarization later on. But let's do reflection and refraction right now. Okay, and we do polarization later on. Okay, so here we go. Notes. Great. So we covered the following sections so far. Okay, 33.2, 33.1, let's put that. 33.2. Maxwell Rainbow that documents the types of electromagnetic waves. 33-3, traveling electromagnetic waves. 33-4, energy transport and the Poynting vector, and radiation pressure. 33-6. Okay, let's do reflection and refraction, and then we get back to polarization later on. Okay, reflection and refraction. And then we're going to have total internal reflection. Internal reflection. Reflection and refraction. We can okay, so let's write that down. This part here is what we call geometric optics. We usually cover that in a different chapter, but Holiday and Resnick, for some reason, we keep it in the same place as electromagnetic waves. Okay, that's what we cover. Okay, what to geometric optics? Okay, what you have to know about geometric optics, okay, that is what we call the postulates of geometric optics. By the same token that have the postulates of electromagnetic theory, right? Have the postulates of mechanics, thermodynamics, and electromagnetic theory. We also have the postulates of geometric optics. There are two, and there are two of them. No, there are more, three. Let me see, three. Let's see here. 1, 2, 3. Yeah, there are three of them, not two. Postulates of mechanics, there are three, right? Second law of Newton, third law of Newton, and the law of universal gravitation. Thermodynamics, there are four. Electromagnetic theory, there's four. And then there are three in geometric optics. There are three of them. And we are going to formulate those three postulates. Let me see, the book, your book doesn't have those postulates formulated here, okay? But it's a good thing to remember where we start from, which is a mistake. Holiday and Resnick, they didn't put the postulates here. For some reason, many books out there at this level, they don't spell out the postulates of a geometric optics, which is a mistake, an unfortunate mistake. Only more advanced books in physics, they come up with the formal postulates of geometric optics. So what are the postulates of geometrical optics? Okay. Light, okay, can be sought. Light, first postulate. First law, postulate or law, okay? Postulates or laws, right? They are synonyms. First law. Okay, light travels can be travels light can be thought as a beam of particles that travels in a straight line. Provided the medium, let's see, does not change its optical properties. Okay. We can also say that if a medium has uniform optical properties, right? Light travels in a straight line. Okay. Another way to formulate this law is, simpler, right? If a medium has uniform optical properties, light travels in a straight line. Or let me illustrate that so you understand what exactly that means, right? You can see that in a laser beam. Right? Everybody has seen a laser beam. Laser beams, they travel in a straight line because in a uniform medium that has uniform properties. And I'm gonna cover this, what property is important. Here you go, let's get that. Is that here? Not this one. Okay, here you go. First part, postulate of ray optics. If you have a source of light, can be a laser, okay? This light propagates in a straight line from point S to point C. Propagates in straight lines from point S to point A. They're just pointing the laser in a different way, right? And so on. The light is not going to propagate in curves like that in this uniform medium, right? It's not going to be circulating like that either. It's going to be a straight line. Optically homogeneous medium. This is what we call an optically homogeneous. Here you go. In an optically, better right, in an optically homogeneous medium, light travels in a straight line. If the medium is not homogeneous, then you're going to see what's going to happen. Light can make curves, a little bends, can be bent a little bit. That's the first. Can you picture that? You see that all the time, right? I think I have a picture like that in my website. Let me show you. I have my own website here. Let's see. Optical devices, waveguide. Here you go. Yeah. Okay, here's my laser beam, my laser pen. See the light beam propagating a straight line. Okay, straight line. Okay, but look at this beam here. Look at this beam of light. You see it makes a sharp turn right in here. This beam that's propagating here, continue propagating in this direction, okay? Similarly, this beam that's propagating here upward, continue propagating in this direction. It's not a straight line at this point. It's only a straight line within this region. It's only a straight line within this region. At this point, at the interface between my plastic, this is a plastic bar, and the air, the beam makes a sharp turn, sort of a sharp turn. Why is that? Because this medium here has different optical properties than the air, okay? This medium alone is homogeneous. The air alone is homogeneous. But going from the plastic to the air is no longer homogeneous. It has different optical properties. But because this is a homogeneous medium, light propagates a straight line. Light propagates a straight line, okay? That's the first postulate of ray optics. Okay. What is the second postulate of ray optics? Okay, the second postulate of ray optics states the type of property. Second postulate, law slash postulate. First law slash postulate. Okay, different media have different optical properties. And this optical property is important, you know. This important optical property is called the index of refraction. And it's usually abbreviated by the letter N. Okay. So the definition of index of refraction, remember that? Refraction is N equal, oh gosh. Let's see, N is equal, oh gosh, I hate that. I'm going to insert this equation here. Yeah. Okay, here you go. N is equal to the velocity of light in free space. C is the velocity of light in free space in the vacuum, divided by the velocity of light in the medium itself. So suppose that I can measure the velocity of light in the plastic. Suppose I can measure the velocity of light in quartz. Suppose I can measure the velocity of the light in glass, in diamond, and so on, in different media, in water, right? Here, this one you already know is 300,000 kilometers per second. Okay, if you can measure the velocity of light in those media, you can get the refractive index of the medium. Okay, in air, okay, C is what? C is 300,000 kilometers per second. Okay, C is the velocity of light in vacuum, 300,000 kilometers per second. Okay, whereas V is the velocity of light in the medium. Can be air, can be water, can be glass, can be plastic, can be diamond, etc. Okay. The refractive index of air. Okay, there's a table of refractive index, indices of refraction. By the way, for the sake of this course, V will always be less than 300,000 kilometers per second, which implies that N is always greater or equal than 1, okay? Greater or equal than 1. That's for the sake of this course. This is not 100% true, but for the sake of this course, it's fine to believe that. Later on, you're going to learn that's not exactly like that. Later on, you're going to learn that there are media with the index of refraction less than 1. In those media, the light is said to be traveling faster than 300,000 kilometers per second. Okay. what is the refractive index for different types of medium. Here you go. That's in vacuum. Refractive index of vacuum is 1. Okay. Refractive index of air is slightly greater than 1. That's why I put, you can check the exact value of index of refraction of air. It's a little bit more than 1, okay? It's 1.000 whatever, you know. Far down the line, you're gonna have a number greater than 1. Here you go in your book, okay? And I'm gonna put here, let me copy this table. Well, I'm gonna do a table right in here. Table. You have a similar table in your book, but I'm not gonna make an extensive table. Here you go. Medium. Velocity of light in the medium. And the index of refraction of the medium. Index of refraction has no unit whatsoever. It's a unitless unit. Has a unitless unit, right? Medium, vacuum. Refractive index is 300,000, like that, meters per second. You count them once, right? You get 3 times 10 to the 8. You go. Let's meters per second. As a result, the index of refraction of vacuum is 1. That you have to remember. It's not difficult to remember, okay? Vacuum. Go 2.5. Make this table looks nice. $288.3. That's good. 3 here. I'll make it 3 as well. 3 inches. Okay, what about air? Air is approximately 300,000 kilometers per second, approximately. But if I'm gonna be picky, you know, and your book has the exact value of index of refraction of the air, you're gonna see it's very close to 1.12329. That's what is in your book. When you do the math, it's a little bit less than 300,000 kilometers per second. What about water? Water has an index of refraction as well, 1.333. It's possible to measure the index of refraction with refractometers, devices called refractometers. Almost any lab has a refractometer. That's the speed of light in water, a little bit less. What about glass? Most glasses have an index of refraction over 1.5. Right? If its index of refraction is 1.5, that means that the speed of the light is going to be 2 times 10 to the 8, 200,000 kilometers per second, 225,000 kilometers per second, 200,000 kilometers per second. And here you go. What about diamond? I talked about diamond. People have measured the refractive index of diamond. The refractive index of high diamond is around 2.5. You know, if you want to make it easier to remember, just remember 2.5. It's not exactly 2.5, it's a little bit less than 2.5, which results in the speed that less than half of the speed of light in vacuum. That's the second postulate of optics. Okay. Geometrical optics. And then we have a third postulate. Third postulate of geometrical optics. Okay, the path of the light in a given medium follows the principle of least time. Okay, not the principle, not the principle of least, not the principle of least space. Okay, you want to put it in. Remember, if you have to remember anything for the rest of your lives in physics, what you have to remember for the rest of your lives are the postulates of physics. So far you have how many you were introduced to? Let's count them. 3, 7, 11 plus 3, 14 postulates so far. Okay, total of 14 postulates. By the way, just to let you know, okay, all those 3 postulates that you see here in geometrical optics, actually, they are derived from the postulate of electromagnetic theory, okay? But we don't do that at this level of the course. Instead, it's better just to, create those postulates of geometric optics, because it's easier to do that than to derive those postulates from the postulates of electromagnetic theory, okay? Principle of least time. So what does it mean, principle of least time? Light is in a hurry, okay? It doesn't matter. A light always wants to take a path that we get from point A to point B in the least amount of time, not in the least amount of space. So let's see what that does it mean. Here you go. According to principle of least time, if you have an homogeneous medium, like this one here, the speed of the light at this point is going to be the same. The speed of the light at this point is going to be the same as the speed of the light of this point, and so on, right? Consequently, in order to travel from point S to point C, the principle of least time, the amount of least time coincides with the amount of least space, right? The distance from here to here is the least space, is the least distance that you're going to get. Light doesn't travel this way in an homogeneous medium. This wouldn't be least time nor least space, right? This is a homogeneous medium. So let's take a look at another example. What about in this case here? What about in this case? You have air and a block of glass, for instance. Okay? If light were to travel in the least amount of space, it would just travel from S to B in a straight line. Okay? But that's not what light does. Light travels within the least amount of space, or within the least amount of time, right? So it's faster for light to get to point B by traveling this distance here in air, okay, which is longer than this one, right? And this distance here in the glass, okay? Why is that? It's because the velocity of the light here in the glass is less than the velocity of light in air. That's what we mean by least time and least space. Okay. This principle applies both to reflection and refraction. What you see here is refraction, but what you see here is reflection. What if you have a light source here that's being reflected by this surface, right? And then you are here located at point A, looking at the light source, the laser beam. Is the laser beam gonna travel this way? Is it gonna travel this way? Or is it gonna travel this way? Okay. Well, going back to the third postulate, it's gonna be the least amount of time. Okay, and the least amount of time is this one that you see here. The angle of reflection is equal to the angle of refraction. Your book called that the law of reflection. It's not a law. It's a corollary of the principle of least time. Okay? Here you go. That's the least amount of time for under reflection. Okay? Angle of incidence, I mixed that up, right? Angle of incidence is equal to the angle of reflection. Okay, this is the second medium capable of reflecting light. Okay, so let's go start applying those laws. Okay, let us apply these postulates to practical situations. Right? Reflection. Reflection of light. The so-called law of reflection is in reality a consequence or corollary of the third postulate of geometrical optics. It takes less time for the light to travel this distance than this distance here, and you can do the math yourself. Okay, let's do that. Let's do an example. Okay, assuming that light travels this way, how long does it take to travel this path here, right? Compared to this path. Let's do that. Knowing the distance between those 2 points and the distance to the surface. Let's do that. Here you go. I'm going to, it's a very simple exercise, you know, confirm, prove that travel light, let's see, no, let's put this way. Example, right? Let's put this way. Here you go. Let a light source be positioned at point S, and a detector, your eye, right, be positioned at point A. Here you go. These 2 points are both equidistant, are the same, are separated, let's see, are separated by a distance d. These 2 points are separated by a distance d. A surface, an optical a reflective surface, positioned parallel to the line connecting S to A is located at a distance L from each point, right? Here you go. Distance, this point is a distance L from the surface. This point is at the same distance L. The distance between those 2 points is D. Okay. Find how long it takes for the light. These 2 points are separated. This D and are located in air. Okay. Find how long it takes for the light to travel through the red path in the figure, right? And here you go. Find how long it takes for the light to travel. 1, through the red path in the figure, and 2, through the blue path in the figure, right? 2 different paths, blue, red, and 3 different paths in this case, but we are considering only this one, assuming that this angle here is at 90 degrees. Makes things simpler, right? Here you go. I'm going to draw that for you. Blue and red paths. This angle here, 90 degrees. Doesn't look like 90 degrees, but let's make it 90 degrees. Is that good enough? Let's see, still not 90 degrees, right? Let's try to make it perfect. Here you go. Now it's 90 degrees, right? Here, the angle of incidence is equal to the angle of reflection. Here you go. I'm going to draw it here. Angle of reflection is equal to the angle of incidence. It's possible to prove it in a more rigorous fashion, and I'm going to do that as a simple example. So go ahead, think how you're going to do that. You know the distance between those 2 points, you know the distance to the surface. Go ahead, use the velocity of the light as being c here and see how long it takes. Using the velocity of light as being c here and see how long it takes, and then compare those 2 results. I want you to do that. I'll give you like 3 minutes. Okay. Solution, right? I'm going to give you the opportunity to do that, and I'll be back shortly. 3 to 5 minutes, and then I'll go call you one by one to see how you did. Okay, I'll be back shortly. Okay, I'm back here. Did you get it? Shouldn't be difficult, right? So let's do the math here. It's just a geometry problem. That's why it's called geometrical optics, because we use geometry, right? In a way, it's rather straightforward. Oh, here goes. So we start with the blue path. Now let's start with the red path. That's simpler. Red path, which is simpler, easier, right? So we have the incident path. That's the incident. This one is easier, right? Path A1, I'm gonna call that A1, A2, okay? A1, A2. A1, length of A1 is gonna be equal to what? D square plus L square is square root, right? The D square plus L square. What did I do here? Square root of that. Gosh, still didn't sunny. Let's see. Okay, good. What about A2? A2 is straightforward, right? It's just L. Path A is A1 plus A2. A is A1 plus A2. Oh, 49. Here you go. That's the one. What about the blue path? More difficult. Okay, is L square, square root of L square plus D over 2 square, right? Twice that. Right? I'll call it S1 plus S2. I'll call that path S. S1 plus S2. By the way, those two paths are equal, so it's going to be 2S1, right? Which is equal to L square okay, here you go. L square plus D over 2 square over 2 square, like that. Now the question is, which is shorter right now? Shorter. Which one is shorter? A or S? A or S? At this point, it's not clear which one is shorter, right? But let's take a look. Let's say, let's say A is shorter. If, in this one, whatever is shorter coincides with or it takes less time, right? The speed is the same, so you don't have to worry about least time. All you have to worry about is least space. Since in this case, light is traveling in the same medium all the time, okay? The amount of least time for one path will coincide with least space for the other, for the same path, right? We don't have to calculate the least time in this case. All we have to do is to worry about least space. That's easier to worry about least space. Here you go, like that. Let's say, S is greater than A. Just let's come up with this assumption that S is less than A, and let's see if it is, right? If it holds true. Let's see if it holds true. If it doesn't hold true, that's because S. Yeah. Let's S is greater than A, okay? S greater than A instead. If it doesn't hold true, then it means that S is the least amount of space, which ends up being the least amount of time as well. Here you go. This one here. That's the question I'm making, right? Is it true? Let's see if it's true. But, just out of the bat, we don't even have to worry about that. You can make it simpler, right? So just out of the bat, we know that this quantity, did I do it right? Yeah, we know that this quantity here is always greater than this other quantity, right? Make sense? We don't even have to worry about that. So no matter what, this pass here is going to be greater than the other, right? But you can go through the trouble of squaring everything and finding out that's not true, okay? I'm going to do that with my software. That's going to take much less time to do it. Here you go, live math. I like software. Algebraic manipulator. Here you go. I'm going to put a...
Professor.
Yeah, yes.
There's a 2 in front of the radical. So it would be 2s1 is 2 times the square root of L squared.
Oh, yeah. That's right. I forgot to put the radical there.
So I think we need to solve this one out.
Yeah. Thank you. Yeah, so we have to put the 2 here. So now it changes the equation, right? Now it changes. Thank you for reminding me that there's a 2 here. I put the 2 here, but then I forgot it. Okay, so here you go. Let's do it here. L square b over 4. Yeah. Here you go. L and then is it greater, right? Greater than the other one, the square root of d square plus L square plus L. Here you go. Save me lots of trouble, right? Because imagine if I do the account or the calculation with the wrong equation, right? So we're going to put like that. I'm going to square both sides, factorize or apply. Here you go. I'm going to square both sides. All right, expand. Here you go. I didn't expand this one. Expand. Ah, man, I hate that. Okay, good. I got it. Now let's expand this one. He did the square here, right? Interesting. He didn't simplify. Let's simplify that now. Here you go. Oh my. Oh, I know why. Yeah. He's thinking that this guy here is a differential. You gotta be careful about those. Yeah, I'm gonna put I'm putting capital D because lowercase d he thinks is a differential. Okay, now I can expand. Yeah, variable. Good. No, he didn't. Why is that? You're supposed to combine those two, man. Here you go. Let's see, maybe it's a collect. Okay, now he did it. Okay. And now I'm gonna put on the other side. Nope. Put on the other side, right? Go expand. You go. Now it's let's see, I can cancel that out. Let's see what else. Ooh, not like that. You know what? I'm gonna apply. It's not clear, right? Whether. Oh yeah, it is clear, right? It is clear, but because this term here is greater than L, right? This term here is greater than L. Because it's greater than L, when 2L multiplies a term that's greater than L, this side is supposed to be greater than the other. So this assumption here is incorrect, right? We can go through the, we can make it even more obvious than that by squaring both sides. Here you go. And now we'll be able to make it clear that that assumption is not correct, right? See, my assumption is resulting in something like that. This term here is always greater than 0. So my assumption must be incorrect. Okay, I'm going to copy and paste that in my notes. Here we go. My assumption of S greater than A resulted in an incorrect result, which means that S must be less than A. Must be less than A. Okay. So that's just a simple exercise that you can do just to verify the amount of list time. Okay. This implies that what the book calls the law. I'm going to put it between quotes because it's not a law of reflection, or theta of incidence is equal to theta of reflection. Easy enough to remember, right? But as a result, is a consequence of the postulate of least time. The postulate of least time also applies to refraction. Okay. The postulate of least time also applies to refraction and results in what the books, not just your book, but every book out there, call Snell's law. Snell's law, okay? And how you haven't taken optics before, right? What the relationship of Snell's law is all about. Here we go. Snell's law is like that. and 1 times sine of theta 1. Oh, I'm gonna call theta 1 incidence, okay? Plus is equal and 2 sine of theta 2. And again, this is consequence of the principle of least time. Let's take a look here now. Let's see, reflection. Oh yeah, here you go. That's an illustration of Snell's law. Okay, this is not the correct one. Okay, let me see here. Here we go. Yeah, here's a derivation of how to minimize LS plus LA. Okay, that's the. So here you go. So here you go. Here is the index of refraction of medium 1. Okay, and that's the angle of incidence. That's what I call theta 1. And that's the index of refraction of medium 2. And the angle of refraction, that's what I call there in the formula theta 2. That's the consequence again of the principle of least time. Okay. So let's just do a quick example, right? Oh, and by the way, let me also illustrate a very important aspect here of this path of the light, right? Remember, light is going from here. That's the direction of propagation of the light. I'm going to put the direction of propagation of the light. Format shape, beginning, here you go. Right, like that, huh? See here. Here you go. I'm going to make it here you go. Okay, that's the direction of propagation of the light here. And I'm going to use, okay, this direction of propagation of the light is in reality the direction of propagation of the pointing vector, right? The pointing vector is propagating in this direction. And because of that, we can illustrate, for instance, the direction of the electric and magnetic fields. I want to do that here in this illustration. Here you go. The electric and magnetic field are always perpendicular to one another. Here you go. Here would be an illustration of the electric field. I'm gonna put that with the red color. Don't forget that E cross B is S, right? E cross B is S. Consequently, the magnetic field is coming out of the plane of this illustration. So I'm going to draw it up, shape, no, circle, and send to the back. No, I'm gonna put it, I'm gonna keep it here and fill it up. I'm going to put no fill. Okay, better this way. And I'm gonna give a color, green color. Yeah, good. Green color for the magnetic field. And now I can illustrate the magnetic field as this green dot. I'm gonna make it smaller. Yeah, here you go. I got it. Like that, right? Here you go. And then a little bit here to the side. I'm going to get a symbol for the E and the B. Let me see here. E and B vectors. Where are they? Where are they? Where are they? Where are they? Supposed to be here. The vector, pointing vector, pointing vector. Huh. Oh yeah, here you go. E, right? I want to copy everything. Place there. E is gonna be red. I'm gonna put bold face, and I'm gonna paste separately. Here you go. That's how you should be visualizing the path of the ray. Light ray. This guy is gonna be my green color. And bold faced. No cross product. Okay. E cross B, right? Propagating this direction. That's how you should be visualizing the electromagnetic field in this ray path. What time is that? 10:52. Let's take another break. Okay, let's see if we have any questions here. Any questions so far? Okay, yeah, it was Mengshu, right? Okay, thank you, Mengshu, and for pointing that out. And I think I forgot. Oh yeah, okay, we're recording here. Let's 10:52. Let's have a break until 11:05. Okay, and then we can come up with some examples of Snell's law. Break till 11:05 a.m. So what you're doing here is reflection and refraction. It starts with the geometric optics. So I see you shortly. I'm back here. Interesting. Okay, so let's elaborate a little bit more on this model here that I'm showing you, right? So let's say the wavelengths. Let's illustrate. Let's keep on illustrating this electric and magnetic field along this path of the ray, this ray path. Here you go. So let's say the distance from here to here is a wavelength, right? Let's say from here to here is a full wavelength. Let's move a little bit further. I need some more space here. Okay. I'm gonna put this guy as a red, as the blue color. Good. So somewhere here in between, I'm going to have an electric field that's gonna point in the other way, and the magnetic field is gonna come into the board, right? Somewhere in between. So here you go. Let me illustrate the. That's what this ray model is all about. That's where, let's see, somewhere around here, right? So my electric field is going to be here, and this guy is going to have a different direction, right? And my magnetic field is no longer going to be a dot. The representation now is going to be what? It's going to be a cross. See if I have a cross here. An X. Here you go. It's going to be like that. Let's see if I can represent this guy with a red, with a green color. Yep, I can. And it's going to be filled up with a no field whatsoever. Here you go. That's the direction of my magnetic field. Make sense? That's the type of model that you have to have in your mind when you visualize those rays, those light rays. You know, geometrical optics combined with wave optics. Okay, I already have my B there, don't need it again. Right? And somewhere here in between those two vectors, we are going to have a node, right? Node right in here, node right in here, okay? If this distance is a wavelength, if we are talking about red light, the wavelength of red light, just consult your book, is around 600 nanometers. So this distance here is very short. If we are talking about red light, blue light would be 400 nanometers. Okay, that's the type of model that you have to have in your mind when you're solving this problem. Okay, so let's continue here. Okay, we're talking about the Snell's law. Okay, well, let's do a simple example. Okay, so here we go. Light is incident from air into a glass of n equal to 1.5. Okay, you have to memorize that the index of refraction of the air is 1. You have to memorize that. That's not difficult. It's not exactly 1, but it's close enough. Vacuum is 1 as well. You don't have to memorize the refractive index of the glass. I will always give that to you. Okay. Light propagates from air towards a glass slab of refractive index n equal to 1.5. The angle of incidence always measured with respect to the direction normal to the surface is 30 degrees. Okay, find the angle of refraction. Okay, so here you go. Solution. Going back to my illustration. Here you go. That's 30 degrees. And I want to know the angle of refraction. By the way, every time that lights go from a medium of lower refractive index towards a medium of higher refractive index, the angle of refraction is going to be less than the angle of incidence, okay? That's implicit in the equation for Snell's law. So let's do that. Here we go. I'll do that here for you. And 1 sine of theta 1 or theta of incidence, oops, equal to n2 sine of theta 2. So you go ahead, substitute. Don't forget, if you're doing that with your calculator, don't forget to convert your angle into radians. 30 degrees is, in radians, is 30 times 2 pi divided by 360. And 1 is 1. And 2 is 1.5. We want to find theta 2. 1, 2. Here you go. Let's substitute that. And 1 and 1 and 2 theta 1. Here you go. So sine of theta 2 is going to be equal to 0.3333. What angle is that, right? What angle is that? Well, you gotta look at the table of sines, or just go to your calculator, right? Here you go. We're gonna get this one here. I'm going to calculate that. I'm getting 0.33984 radians. Okay. And 2 here that you see here is an integer number, okay? Can be 0, 1, 2, 3. Here's the other possible solution, right? But we're concerned about this one here. So we gotta change theta 2. We're gonna use this solution here. That's one solution in the circle, trigonometric circle. That's another solution in another part of the trigonometric circle. Okay, we want this solution here, but we want the solution in degrees. How do you find? We multiply by 360 divided by 2 pi. Calculate. I'm getting 19 degrees, 19.4, 19.5 degrees. Okay. That's the solution. I'm gonna eliminate this one so you don't get confused, okay? I'll copy that and paste into my problema. Here you go. 19.47 degrees. .47 degrees. That's what we have, and then we can move forward in something else. So here you go. Law. Here you go, of reflection. We did that. All right. Law of refraction, or Snell's law. Both of these so-called laws right? And be derived from the postulate of least time. What else can we do? Okay, so here you go. That's an important. I don't want this drawing. I want. Okay, yeah. So suppose now that your light source is inside a glass or inside water, let's say. Okay. What do we find when we shine a light source, a laser beam, for instance? If the light beam is going from a medium of higher index of refraction towards a medium of higher index of refraction, the light moves away from the normal, okay? Towards the normal, right? Towards the normal, from lower to higher, away from the normal, from higher to normal. This is nicely illustrated here in this figure. Okay, so let me see here. Yeah. You are underwater, you are shining light in the vertical direction. Some of the light is reflected, yes, but some of the light is also, most of the light is transmitted. Okay. Just going back to my drawing that you have here, remember? Here you go, the light beam comes towards the interface of the air with the plastic, right? That will be the path of the beam. But because the plastic has a higher refractive index, light bends towards the normal. That's what you're having here. Now, when this light beam reaches the other interface, instead of propagating a straight line, it's going to bend away from the normal. And this angle is going to be, depending on the angle of incidence, of course, is going to be given by the Snell's law. Note, see that not only we have light being refracted, but we also have light being reflected. See that? That's the first reflection. The picture picked that up very clearly. Similarly, the refracted light gets reflected here. Not everything gets reflected. Do you see this intensity here is lower than this intensity, right? But something also gets refracted. And so on, right? Reflected, refracted, reflected, you know? Incident, reflected, incident, refracted. Whatever was reflected here gets refracted here as well and gets reflected here. Picture that I took with my camera. Okay. Now, what if you put your thing here inside your water, right? You can observe something like that. Transmitted and reflected. At a different angle, you're going to get transmitted and reflected. Well, it happens that as you change the angle, you get more and more light reflected, okay? Not only that, but the light ray that is refracted increases further and further, moves further and further away from the normal. Let me put a little bit steeper. It comes to a point that the refracted light doesn't have anywhere to go but just to be refracted parallel to the surface. We say that refracted parallel to the surface. It's not exactly like that. No, no, no. What exactly happens is that there is no refraction at all, and all light is totally reflected. So I have to remove that guy. Okay, I'm gonna put even better. I'm gonna put like in dashed line, a dashed line here. It's better if I put dashed because there is no refracted light parallel to the surface. Everything is reflected. This phenomenon here we call total internal reflection. Going further that, we get reflected again. Very important for practical applications. So let's talk about total internal reflection. Total internal reflection, TIR. Okay. Whenever light propagates inside a medium of higher refractive index towards another medium of lower refractive index, you may have total internal reflection at this interface. What does it mean, total internal reflection? Depending on the angle of incidence, you may have total internal reflection, TIR, at the interface. This can be the angle of TIR can be calculated, the minimum angle, okay? The minimum angle of incidence or total internal reflection can be calculated using Snell's law. Okay, how do we do that? Let's go back here. Snell's law, right? N1 is the medium of incidence. And here is the angle of incidence, the angle of refraction. For, here you go, angle of refraction equal to 90 degrees. Here you go. Like that. I'm going to go for the next step. 90 degrees. Okay, thank you. Go. That's going to become 1, right? We call that the critical angle, the minimum angle of incidence for TIR, the so-called critical angle. Can be calculated, right? Using Snell's law. I'm going to put differently here. Here you go. I'll do like that. And then I will rename theta 1 as being the critical angle. Okay. So critical angle becomes N2 over N1. It all depends on the refractive index. Okay. So, example, any angle above that, you have total internal reflection. Any angle of incidence, any angle of incidence above, for any angle of incidence above this value, you have TIR, total internal reflection. And then we can do another example for water, and equal to 1.33, right? Find the example. Find the critical angle for water. Find the critical angle of incidence for air-water interface. Okay, N1 is equal, N equal to 1.33, right? Solution. And then we can do that with my software, right? Go here. Copy this guy here. N1, theta critical, N2 is 1. In this case, N2 is 1. This one is going to be pi over 2. N1 is 1.33, N2 is 1. We want to find it theta critical. Substitute those numerical values right in here. Solve for this 0.75. Let's see what we get. Okay, what matters is this solution here, not this one. I'm going to erase this one here so you don't get confused, right? We go theta critical. I don't need that solution either. Arc sine of that, clarify, calculate 0.85. And now if I want to determine the angle in degrees, we get something like that, 2 times pi. Don't forget, most software there, they just give you the value in radians. So we get 48.7 degrees, 75 degrees. Solution. The result is 48. The solution is 48.753 degrees. It's 11:29. Let's see here. We are almost done with this chapter 33. I want to update my syllabus. Yeah, we couldn't get into images yet, but it's going to be rather straightforward. Yeah, so we're still ENM, right? And geometrical optics. Can I do that? Geometrical optics? No. Let's put it this way. Lab 4. This one is going to be my version 5. Go. Save that as well. Any questions about that? Let me pause my recording as well. Good. So what we did before, right? The previous virtual lab. Yeah, there you go. Previously, it was F versus 1 divided by n squared. now it's going to be F versus L prime square. Remember L prime is the length of vibration, the vibrating length. We can do that in the lab rather easily. Here you go. The vibrating length is this one. L is this one here, is this length. So we can change the position of the vibrating fork to change the vibrating length of the string. Okay. But before we go forward, right? And remember also the equation. What is that? Yeah, the wavelength is a function of L prime, right? So here you go. When we do all the math, the mathematics, here's the force and here's the vibrating length of the string. We should get a slope that's proportional, a straight line with a slope that's proportional to this relation. Okay, so let me go get your data. Spreadsheet I started. As you can see, here you go. As you can see, I already downloaded your data for the lab number 1. I started correct. Oh, that's not this one. Sorry, that's 2020. Let's see, spreadsheet lab. Yeah, lab reports, right? Here you go. I downloaded already our spreadsheets, and I'm gonna, I'm gonna correct it. And I'm gonna correct that today, even today, and I'm gonna post that in your webs in the group folder. Okay. Now let's take a look at your data. That should be lab 6.
Professor,
Yeah,
I just have a quick question. Do we have an exam on Wednesday or Thursday of this week?
Thursday. The exam is Thursday. Here you go. Let me show you the syllabus again. Only the first exam was on Wednesday. Okay. The remaining
perfect.
exams are gonna be on Thursday. Here you go. Let's remaining exam.
Thank you, Professor.
Exam 2, right in here. Gonna be on Thursday. And let me just make sure those are the right, is the right data. L prime, that looks like good to me. One more student coming in. Yeah, that's good. Next. One here. Good. L prime, yeah, that's L prime. See, you're gonna plot those 2 columns, right? Okay, I will upload. Go to Drive. Summer group folder. Don't forget to change the number of your lab experiment, right? This one's supposed to be 4. I put it 6 because it was a previous semester. Wait a minute, is that 6? Make sure here one thing. Notes. No. Syllabus, that's here. Lab 4. Why is 6? Let me check one thing before I move forward. Okay, yeah. Change to 4, please. Group, not this one. Oops. Group 1, group 2, group 3, group 4, group 5, group 6, group 7, and group 8. Okay, first thing first, right? Lab notes. One. I uploaded the data into your group folder. Okay, before you download the spreadsheet, please change its name from P39, right? L06 group whatever, right? To P39 L04 group whatever, right? Let's copy it. Capital Y. The instructions are rather similar, right? That you had there before. Okay, report for lab 3 is due the day after tomorrow. I didn't tell you that, right? So let's do. Okay, upload the report for lab 1. That's good. Before you download the spreadsheet, please change, rename it from L06 to L04. Now download the spreadsheet. The graph that you're gonna plot is gonna be different. Mg versus L prime square. L prime square. Right? Times Neuroman. Okay, good. Remember it. Paragraph. How do I remember it? Huh. Restart. Continue numbering. Huh? It doesn't continue numbering. Strange. You don't need that. Work on the units. Huh. Plot, log the slope, right? of the slope. Less stable. Work on the units. Work on sig fix. Fill up the, is that the third table? No, that's not what I want. One, two, three. Yeah, that's the third table. It's very similar to the previous one. The format is very similar. And let's go step by step how this whole thing works. Right? Waves and disturbance that propagates in a medium. A medium can be string, air, solid, metal, vacuum, etc. You can generate a wave in a string by moving string up and down with your hand. Sound is a wave that propagates in the air by vibrating the string in the vocal cord. You can generate a sound wave by creating regions of higher and lower pressure. That's what the string does, right? Here you go. The moment I'm moving my hand, if I move my hand this way, I produce a sound. But my hand is producing a sound of 5 hertz. Because I'm a human being, I cannot hear the sound. As human beings, we can hear only sounds of 20 hertz, right? And the moment I push my hand in the air like that, I'm compressing the air. Okay, the moment I push my hand away, I am creating a region of lower pressure. And it's those regions of higher and lower pressure that produce sound. Okay, vacuum. Oh, we want to go. That's everything. We covered that, right? Okay, so what we have to talk about? We have to talk about the velocity of a wave in a string. This thing can be F is a tension. We covered that as well in the previous lab, right? Mu is the linear mass density, mass of the string divided by the length of the string. Okay, so here we go. Here's the equation that relates the wavelengths with the velocity of the wave, the wavelengths and the period with the velocity of the wave. Okay, the standing wave is generated here in this region. It can be a wave like that with only 2 nodes. It can also be a wave like that with 3 nodes. It can be a wave with 4 nodes, right? 5 nodes and so on. Okay, raw data, mass of the string. We have a scale that has a resolution of 100 of a gram, producing 5 decimal places in the kilogram scale, the kilogram unit. Mass of the hanging mass that's going to produce this hanging mass produces a tension in the string. L is the total length of the string. Measure is a ruler. L prime is the vibrating length of the string, and the wavelengths you also measure is a ruler or the ruler or the meter stick. Same here, ruler or meter stick or meter stick. They both have the same resolution, but one is longer than the other, right? For a single lobe of vibration, we have L prime equal to lambda over 2. 2 lobe of vibration, 2 lambda over 2, 1. See, 1 lambda over 2, 1/2, 2/2 of wavelengths, 3, 4, 5, and so on. That's what the wavelength is. So don't forget, there is a difference, right, between L prime and L. L prime is the length of vibration. L is the total length of the string. Length of vibration Total length of the string. Okay, here goes velocity lambda over t is equal to that. We use the relationship between lambda and the mode of vibration. Okay. We have this equality here. We can square both sides. And that's what we end up getting. What we're going to do, we're going to change this factor here, this independent variable. That's what we're going to change. And then find out what is the weight that produces a resonant mode in the vibration of the string. Can you picture that? Right? So you let's get my one of the, here you go. L is here. Here you go. So I choose some lengths here for this. Nothing to, yeah, I choose some length of this string here, right? And the students go and find out which weight, which mass, which tension produces the first mode of vibration. Oh, wait a minute. Produces, no, yeah, that's right. So what am I doing here? I am fixing the mode of vibration, the fundamental mode, okay? We are using a fundamental mode only for this experiment. You know, I start with a length and find out what's the weight it is. It's easier to perform the experiment with the fundamental mode. It's easier to see it. If you see just a single lobe vibrating, there's the fundamental mode. And you go ahead, increase the length of the string. Find out what is the mass. We use slotted masses for that. Okay. Then increase it. 142, 1 meter, 122 meters, 142 meters, and so on. Right? And you find out the mass for a single mode of a vibration. The frequency is not changing. The mass of the string doesn't change. The length of the string doesn't change. This value doesn't change. The frequency doesn't change. Consequently, the linear mass density does change. Okay. So plot mg versus L prime and determine the slope. You log the slope right in here. Don't forget the units. Right? When is the lab due? When is this lab is going to be due? Let's see. This one, due date for this lab. Let's make it due on lab notes. Lab note. This one here. Lab report. Lab 4 is due. Oh, let's make it due on Thursday. Okay. Report of lab 3 due on Wednesday. Okay. I'll give a little bit more of time for that, right? The day after tomorrow, since I didn't announce. Ideally, it should be due today, but I didn't announce, so I'm going to give you another 2 days. And then you, since those two labs are similar, I'll give you just one more day to work on lab 4. Let's take attendance. We have 31 students only today. Okay, lab. Today is the 27th. 22. Let's see, 23. Okay, what I have here. 23. Yeah, 26 was yesterday. Yeah, today is Monday. 26, 27. Good. Brian Espino, are you there, Brian? You're recording. Yep. Brian, I don't see Brian there. Toby, are you there, Toby?
Yeah, I'm here.
Okay, next, Pedro Flores. Okay, thank you, Pedro. Lawrence Flores.
I'm here. Prof.
Okay, thank you. Kenny Villagomez.
Yeah, I'm here.
Next is Nolan Williams. Thank you, Harun Atif.
Here.
Okay, Musa Atif. Who's coming? I don't hear you, Musa, if you're here. Okay, I'm gonna put star. Daniel Nwagbo.
Yeah.
Okay, David Nwagbo.
Yeah.
Next, Zachary Blue. Are you there, Zachary? I see you listed here, but I don't hear from you. Okay, star here. And Elena. Oh, Musa, okay, it's Musa. What about you, Elena? Are you there? I don't see Elena in the list. Luis Crystal, you just joined.
I'm
right?
here.
Okay, David Maes. Thank you. Robert Faust. Next is Daniel Frady.
Here.
Next is Olivia Kruger. Chuck Lu. Are you there, Chuck? Chuck Lu. Okay. Oh, yeah, good. Thank you. Amalia Gale.
Hello, Professor.
Hello, thank you. Tiffany Wang. Anthony Lopez. Next is Shaq Tafi.
Here.
Thank you. Daniel Yang. Daniel Yang. I see Daniel. Okay, I'm here. Okay. Okay, Ryan McNeil. Are you there, Brian? Okay, good.
Professor,
Yeah, is that
I'm here. Zachary.
Zachary?
I
Okay.
was in the bathroom. My apologies.
Okay, here you go. Zachary. Claire. Claire. Okay, thank you. George Risk. Thank you, George. Jennifer Ramirez. Noah Raymond.
Here.
Okay, Natalie Santiago.
Here.
Okay, Meng Shu. Okay, good. Meng Shu. Nathan Silva. Sarina. Sarina Alexis Negret.
Here.
Next is Darnis. Thank you, Darnis. Olivia Song. Is Olivia Song there? Okay, no, unfortunately. Yeah, let's see how many students we have. 32, yeah, 31, that's good. 32 here, let me see. Yeah, 32, that's good. We're in good shape. And so you know what to do, right? Can you So go ahead and start and plot your graph. Let me, in this meantime, I'm going to look for a video in YouTube that I saw it was pretty good that showed this experiment, okay? Let me look for it while you work on the graph and other stuff, okay? Let's see, waves. String. Standing waves experiment. Okay, here you go. I got one.
So what we have here is a frequency.
Okay, so I'm going to start sharing the screen with you. This guy here you go.
So what we have here is a frequency generator.
Okay, this frequency generator is something that you can find in any electronics lab. And then what he has here is like a speaker, okay? A speaker that moves back and forth, attached to a little alligator clip that clips the string. Or even better, he didn't do that. He didn't clip the string. He wrapped the string around this we gotta look more carefully. It's like a little bolt that attached to the speaker, okay, and it moves with the speaker itself and vibrates up and down.
Connected to what's called a wave driver. It's just a speaker. It's going to pump up and down at whatever frequency I set this guy to. When this guy pumps up and down, well, he sends a wave. Sends a wave down to.
So you see, this one is the vibrating source, okay? And the driver here is, like I said, is a device that can produces vibrations of different frequencies.
This end, the wave reflects, comes back. Now, if I set it to just any old frequency, let me just turn this on.
Here you go.
Well,
See the little thing vibrating up and down?
So it's sending waves back and forth.
At this very moment, we do not have resonance in the string yet because we don't see a clear mode of vibration there.
But these waves are out of sync.
Okay.
They're not exhibiting consistently constructive or destructive interference at any one point.
So
but if
you have to adjust to a proper frequency to get a clear mode of vibration there, resonance.
Set it here.
Here you go. So here you go. It's getting there. Here you go. Too low. See that?
I have what's called a standing wave.
That
is
now he got the frequency.
That's sent down and reflects, constructively interferes with the next wave that comes down right at this point.
Not every frequency generates a standing wave, okay? Not every frequency generates a standing wave for this length. So we say that the standing waves has, let's say, quantum frequency, discrete frequency, that would be the proper word for that, has discrete values of frequency. That's how the standing wave, you cannot get any type of frequency to get it. Solenoid to you. Well, what you have here is a speaker, okay, Faust, Robert, is a speaker that's connected to this guy here. And I can show you one of those. It is a speaker. Yeah, it is a speaker. If it has a solenoid there inside to make it move up and down, that's another story. Okay. So here you go. Let's continue here. Is this here you go?
Waves that reflect, that come down and reflect, destructively interfere with the incoming waves right here, and that's called a node. I can touch it, and it still is working. So the node is not moving. Here it's moving up and down, and here it's moving up and down. And we'll see that in a second with the high-speed camera.
Here you go. That's the high-speed camera. You can see the lobes more clearly without the high-speed camera.
Second harmonic. The second possibility for a standing wave.
Now, take a look here. See, there is a node right in here. See that? There's a node right in here. We have the vibrating device right in here that has a little bit of a amplitude. You always see something like that in the experiment. And it generates one node here, another node here, and another node at the other end. This end is not fixed, but the other end is fixed. This end is not fixed because that's the one that's vibrating up and down. That's the one that's vibrating up and down.
String that's held at both ends. Because notice this is a node, this is a node, and the middle is a node. So we have 3 nodes for this. Now, like I said, second harmonic, well, what's the first one? The first one,
the wavelength should be a distance from this node to the other node. So we measure this length with the meter stick. Okay, for today's experiment, we are going to excite just a single lobe. Okay, let's continue here.
will be half this number, so 8.5.
There you go. That's the fundamental frequency.
And there we go.
That's the fundamental mode of vibration. High-speed camera. You can slow
Basically the
down.
scenario of a jumper. Now, I can find any of the other all of the other harmonics are multiples of this number. So we just saw that 2 times this number was the second harmonic, or the second possibility. Well, if I go 3 times this number, I should get the third harmonic. Well, 3 times 8.5.
Yeah. That's the experiment that we did last time, right? That's the experiment that we did last time. He's not varying the length of the string in this case. Here you go. 3 modes, 3 lobes,
So
not
that's
3
the
modes.
third harmonic. How many wavelengths is this? Well, it's 1 1/2. 1 1/2 wavelengths. And
One.
it's easier to see.
Here you go. The way I like to count is like that. 1 1/2, 2 1/2, 3 1/2. That's how each lobe is half of a wavelength. That's the way I like to count it.
High speed. So check out this shot with the high speed camera and verify for yourself that it is 1 1/2 wavelengths. So again, third harmonic, 1 1/2 wavelengths. Well, let's go to the 6th harmonic. The 6th harmonic will just be double this frequency. So we go up to 50.
Here you
And
go.
there we go. That's the 6th
1,
harmonic.
2, 3, 4, 5,
And
6.
it's 6 times the fundamental frequency, which we measured in the beginning to be 8.5 hertz. So check this guy out. We have 1, 2, 3 wavelengths. And in the next video, the explanation video, we'll go through the calculations and the derivations.
Okay, so. That's the type of experiment. That was for the first experiment. So let's stop that. Let's go back here and let me see if I can find one with a speaker. Go ahead, keep on doing that while I look for, oh, here you go. Here is the device, okay? A closer look at the device.
This is experiment number 3,
This device we buy from Pasco, but you can also use a speaker.
the waves on a string experiment. The hardware consists of a piece of string, a pulley, a weight hanger, and a bunch
Yeah,
of weights.
That's how we usually do. That first video that you saw, we don't do the experiment this way. We do exactly in this way that this guy is doing. Okay, so here you go. We have the hanging mass.
Okay. A weight hanger,
Okay, and we have the pulley, just like I drew there. The string,
and a bunch of weights.
the slotted masses.
A mechanic.
Oh yeah, that's the device. See the speaker that I'm talking about. Is this one right in here, and we have this guy attached to this vibrating device that's moving the string up and down. That's the
Drive or vibrator, which is basically just a coil and magnet loudspeaker, a function generator, and a power
it
amplifier.
does have a coil there because
and
it's a
a
speaker.
strobe to stop the vibrating motion of the string.
So we also use this strobe there in the lab, and we can adjust the frequency of the strobe. Okay, we turn off the lights of the room. Okay, put the string to vibrate. There are two ways of doing this experiment. Okay, either with the strobe or with that frequency generator. The frequency generator already gives you the frequency on the screen, right? The other, for you to find out what's the frequency of vibration. The other way is to use the strobe. If your frequency generator doesn't have the frequency they're displaying for you, you just use a strobe to freeze to appear the string to be frozen, right? And the strobe is calibrated to flash at a given frequency. That's one possibility.
For anybody who's interested, this line that you see moving up and down is caused by the rolling shutter of the camera.
Linear
We measure a
density.
piece of the string.
Okay, here you go. That's what we do, exactly what we do. We get the string, 1 meter, 2 meter long, put in the scale, we get the value of the mass of the string. I should have shown that to you last time, right? Here you go. Here you go. Here's the mass of the string. The length of the string, we measured it as well. And from those two values, we get the linear density of the string.
1.31 grams. Measure the length of the
Here you go.
string.
Length of the string.
1.095 meters.
Okay, that first video that you saw was a more qualitative video for the experiment. This one is a more quantitative. It gives you the exact step-by-step procedure, right? And the measurements.
And calculate the linear density of the string. 1.31 grams divided by 109.5 centimeters, which is 0.01196
That's done by the spreadsheet automatically.
grams per centimeter, or whatever units is appropriate for the experiment. Make sure you measure the distance from where the string contacts the pulley to where it contacts the mechanical vibrator.
Yeah, you got to be careful about that, right? Because you have to observe where the nodes fall. The node is not going to fall exactly here. The node is going to fall nearby this point where the string is vibrating. The other node there, the other node is going to fall exactly there at the point of contact of the pulley.
So with 400 grams of weight on the hanger for a total of 450 grams, I've adjusted the frequency of the mechanical vibrator until I get 2 loops on the string.
Okay, here you go. One loop.
There's the first loop, the node, and the second loop. The frequency of vibration is 31.4 hertz cycles per second, which corresponds to 2046 cycles per minute, or RPM on the strobotach. So
okay, that's the strobe is on. Okay, that's the strobe is on. The strobe is not completely synchronized with the vibration of the string. That's why it's moving a little bit back and forth. Okay, there's a little bit of a ghost here image, right? because of this lack of synchrony.
Well, I'm adjusting the frequency on the strobo tap
Here you go.
until I freeze the string.
Okay, here you go. Almost there, and didn't get there yet. So that's how you find out the frequency using the strobe. The other way to find out the frequency is just by using that frequency generator that display the frequency that the generator is generating. You gotta make sure that both the strobe, if you're performing this experiment, right, either with the strobe or with the frequency generator, you have to make sure that both instruments are well calibrated so you get a good result. Higher modes, you go.
3 loops with 2 nodes. 4 loops with 3 nodes. Here we have 5 loops and 4 nodes. Now, the higher modes get more and more difficult to drive. I'm trying to get 6 loops.
As we increase the number of modes, it becomes more and more difficult to see it clearly, because as we increase the number of nodes, okay, the amplitude becomes smaller. So we go up to the 6th mode of vibration. That's exactly what he's saying.
Loops here, but what's happening is I'm only getting 3 definite loops. It's trying to form nodes here, here, and here, but there's a parametric excitation going on that causes us to drive the 3-loop mode at the 6-loop frequency.
Okay, so that's one more video that we have here. And let me see if I can find the speaker. Here, the device, okay. Pascal cell, those things. Not every college has this mechanical vibrator. That Lake Harbor College, we have just one mechanical vibrator of this type, and we cannot perform with it. So we use instead a tuning fork that's set to the frequency of vibration of the power line around 50 to 60 hertz. Okay. Maybe it's this one. Oh yeah, here you go. That's the one I was looking for. Okay, here you go, the speaker. Okay. So what this speaker is made of? Okay, yeah, we do have a solenoid here in the speaker. We have a magnet and a solenoid. But the easiest way for you folks to understand is to visualize the speaker, right? So here you go. We can connect this speaker. One day I was looking for a speaker like that so I can do the experiment. It's not easy to find those speakers, by the way. You can connect those speakers to the function generator.
The way to look at resonance
right?
is to look at what are called modes of vibration on a string. A mode is just a frequency at which a string, like the one shown here, wants to vibrate naturally in exactly the same way as a simple harmonic oscillator wants to vibrate naturally at some frequency. What we have here is a string that's anchored on one end. On the right-hand side, you can see it's tied onto a clamp that's clamped to the table. And on the other end, I've attached it to...
In this case, they cannot find out the exact tension in the string because they don't have a mass attached to that. They just connected it with a given tension. So you cannot change the tension, right? Because you do not have a mass hanging through it. It's not a good way of doing the experiment in a quantitative fashion, but it's a good way to demonstrate the experiment.
What used to be a perfectly good mid-range driver and now won't work very well ever again. We'll see in a minute. I'll zoom in on some of the details here to see how this thing is going to work. But the idea is that we're going to use the mid-range to inject energy into the string. We're going to move it at different frequencies and see what happens, see how the string behaves if we move it at a very specific and a well-chosen and advanced frequency to see if we can force it into behaving as it normally would when it's ringing at one of its modes of vibration. So you can see here, this is a close-up of what I've done to that poor mid-range. I've glued a post, in fact, it's just a wood screw, onto the dust cap of the mid-range. And I glued some small sticks on there to keep it upright because the string is pulling it sideways a little bit. What we're going to do is move that driver, the loudspeaker, up and down. And that's going to, of course, move the string up and down, as we'll see now.
Here you go.
So here we can see what's happening. I'm driving the left.
That's a low frequency. We can see it by the naked eye. That's moving up and down. I suspect that should like a 2 or 3 hertz.
Loudspeaker with an amplifier attached to an oscillator. The volume of the amplifier determines the amplitude, so how much the woofer is moving up and down. And the oscillator I then use to determine the frequency, which is how many times per second it moves up and down. And as you saw a minute ago, the other side of the spring is attached to a clamp. I can change the frequency. This is 5 hertz.
Changing the frequency.
This is something like 10 hertz.
10 hertz now. So he had 5 hertz before.
Going up and down.
Okay.
Or I could go the other way. I can go back down to 5 hertz. That's 5 hertz right there. Or I can go all the way down, for example, to 1 hertz. So this is moving up and down and back up again 1 time per second.
Source of vibration.
System again. I'm now driving it at something like 5 hertz, 5 times per second, and I'm going to increase the frequency bit by bit. This is maybe 6, 7 hertz, up to 8, 9 hertz. And suddenly you'll see when we hit 11 hertz, which I've already found out to be a magic number, what will happen is that the string will suddenly behave differently.
Okay, here you go.
Hertz,
we are reaching
and this is 11
resonance.
Hertz right
Resonance of the string.
Freeze this. The string is in what's called its first mode of vibration. This is the frequency, 11 hertz.
11 hertz right here at the bottom.
In this particular setup, this is the frequency it wants to resonate at, the lowest one, this 11 hertz, so 11 times per second. What you can see is that even though we haven't changed the amplitude, the amount that the driver, the woofer is moving up and down, the amount that the string is moving up and down in the middle has changed dramatically. And that's because it wants to ring at this frequency. Let's start the video again and see what happens if we increase the frequency again. So this is 11 hertz. Let's move it up. This is going up to something like 15 or 16.
Next frequency should be around 22 hertz.
Let's see.
Next frequency
Right
of resonance.
So we've changed now, we're moving faster. Still.
So we are not in resonance right now, okay? Because you cannot see the next, the 2 lobes here.
Put the same amplitude on the woofer. Now let's go to 22.
Oh, okay, here you go, 22 hertz.
At 22 hertz, and remember our first mode of vibration was 11 hertz. At 22 hertz, you can see what we have here is the second mode of vibration. So this is the.
So don't forget, right? When you perform the experiment, you gotta be careful to choose exactly where the nodes is. In general, we say that the node is located here at the point of vibration, but it's not correct. Okay, it's very close, but it's not correct because it is a point where the amplitude is not 0, right? In this specific case, a node should be a little bit to the left here. So it's more reliable to measure the wavelengths, actually the half of wavelength from this point here where you clearly have a node to this other point where you also have a node. It's the end of the string is at the rest.
The next frequency up that the string wants to vibrate at, 22 hertz is 2 times 11 hertz. So it's twice the frequency of the first mode of vibration. You can see again, I've frozen the video here so you can see what's going on. What's happening now is that the string naturally stops vibrating in the middle, but we still have 2 large excursions, 2 points where it's moving much more than the woofer is on either side of that point where it stopped. But this happens naturally. I haven't done anything to the string to make this happen other than to put in the frequency where this mode wants to vibrate.
Okay, going back to that other video that I showed to you about the electromagnetic wave, right? In which we had that electric dipole the electric dipole, that was being driven by the device there in the video was somewhere, suppose that this thing here is the electric field, right, of your electric dipole. So in that experiment, the antenna that you saw there would be this lens right in here with a maximum amplitude of this spot and a maximum amplitude of this spot. As you remember, as the guy moved around the fluorescent lamp, the fluorescent lamp became much less brighter here at this point, a point that would correspond to the node of the electromagnetic radiation, right? So what you see here is a visualization, is a very reliable visualization of an electromagnetic wave, a standing electromagnetic wave with maximum amplitude here at this point in the antenna, and another maximum amplitude here at the antenna, the other end of the antenna, and a node here in between. It was the second video that I showed to you today, right?
So let's start the string moving again. I'll start the video moving again, and we can see what happens if we keep going up in frequency. So this is still 22 hertz, and then we changed it something like 25, 26 hertz.
Yeah, look what happens. The amplitude decreases. It means that at 25 hertz, you do not have resonance for this string.
And we lose that resonance. Now let's go to 33 hertz, which will be the
If you go
third
to 33
mode of
hertz,
vibration.
yeah, here you go.
Here we are.
Okay, you can have phenomena like that for electromagnetic waves as well. Okay, Hertz, when he was performing his experiment, he was using his ring device to find out those places where you had a node, where you had maximum amplitude, and so on, just by observing the sparks between those two spheres. So this one is a very good analogous. Don't forget, this one is a very good analogous for electromagnetic waves. Why is that? Why is a very good analogous? Because electromagnetic waves are transverse waves, and this model here is also a transverse wave. They are not exactly the same phenomenon, but it is a very good analogous.
See what's going on here. It's basically the same thing again. We have a frequency coming into the system, still at the same amplitude, but now the string naturally wants to resonate at this frequency. But in order to do that, a smaller section of the string has to be vibrating. So it naturally stops vibrating in those two sections you can see there in the middle. And we have these three areas where the string is vibrating up and down more than the amplitude that we're putting in from the woofer. Let's start the video again and go higher in frequency. This is 33 hertz. Let's go up to 37, 38 hertz and up to 44 hertz. Right there.
You go, 44 hertz. Do you notice that the amplitude is decreasing, right? As we increase the frequency.
So 44 hertz, we have the same behavior again. Now we have.
So as we increase the frequency, it becomes more and more difficult to see those standing waves.
3 points on the string where it's not vibrating, and 4 points where it's vibrating more than the amount of energy that we're putting in, or the excursion that we're putting in using the woofer. So this will keep happening as I go up in frequency. It's 44 hertz. If I multiply the original by 5, I get 55 hertz. And of course, you can see it's the same behavior.
1, 2, 3, 4, 5, 6. Now 66 hertz
on this, and we'll see that that in fact the string really isn't moving. In a perfect world, it's not moving at all at one point. It's completely still. Of course, this isn't a perfect system, so there's a little bit of movement there. You can see the blurring on the points where it shouldn't be moving. And if we then change the frequency back down to say,
there is a little bit of movement because he didn't get the exact frequency. Okay, that's basically what's happening here. Either that or because some other reason.
33 hertz, this mode goes away and it automatically settles into its third mode of vibration. So the thing to remember is that the string wants to do this. So if we had hit it with an impulse, if we had plucked it like a guitar string, all of these modes would be singing together at the same time. And that's what gives a guitar string the characteristic sound that it has. It's the combination of all those frequencies playing together simultaneously at different amplitudes that makes the sound of a guitar or a violin or a harp or a piano, barring any small details about tuning. That's what the balance or the relationship between the amplitudes of those different harmonics playing together at the same time
There you go.
is what makes those.
Today's experiment, we're exploiting only this mode of vibration, right? And what we are doing, we are reproducing this mode of vibration for different lengths, L prime. We keep the same frequency, change the length L prime, and in the process, we also have to change the tension in the string. In this case, he's just changing the frequency to get different wavelengths for the same lengths and the same tension in the string. That's what he's doing.
Those instruments have their characteristic sound.
Okay, so let's close this one. So let's see how you're doing with the spreadsheet, right? Plot. First thing I want to know is you plot don't forget, like there will be like 1 or 2 or 3 questions of whatever I am showing here to you, okay? In the exam, for the exam. Toby, did you plot the graph? Toby, are you there? I'm gonna put a question mark here. Toby is away from his computer, right? Here you go. Next, Pedro, are you there? Do you also need to change the table names in the spreadsheet number 4? Table name, let me see how the table is. No, the table names don't need to change. No, there's no need to change that. Okay, Jennifer? Just change the title of the lab to L04. Leave the table number in there. This table number relates to the chapter in my lab manual. Okay, so no need to change, but please change the L0, put L04 here, so I can keep it that in my. Pedro, it doesn't look like Pedro is there either, huh? I'm gonna put you here.
Oh, hello.
Oh, you're there. Okay, do you plot the
yeah.
graph?
Oh, yeah, I'm still working on it, Professor.
Still working.
Yeah.
Okay, thank you. Lawrence? Are you there, Lawrence?
Not yet. I'm still kind of working on it.
Okay. Kenny, are you working there or what you're doing?
Yeah, Professor, I'm still working on it.
Okay, where is Toby? Is Toby there? Toby, I'll give you another opportunity here. Okay, I'll keep the question mark there. Nolan, are you there?
Yeah, I'm here. I'm still working.
Working, okay, good. Harun, did you plot the graph?
Yeah.
You plot, okay. What are you doing right now?
I'm done with it.
Oh, done already. Okay, let me put it right there down here. I'll get back to you, but what about Musa? Don't go yet, I'll get back to you soon, okay? Musa, are you there? Okay, Musa, I can't hear you. Next, Daniel.
Yeah, almost done. We are working.
Almost done. Okay, so you plot the graph?
Yeah.
Okay, so what are you doing right now?
We are checking the sig figs and all that.
Okay. Dave? Are you there, Dave? Almost done? Okay, so you plot the graph, right? Almost done. Okay, next, Zachary.
I'm still working.
Still working, okay. Elena? Is Elena here? Elena is not here. Okay, next, Crystal? Are you done with the graph, with the plot of the graph, Crystal? This was okay. I can't hear you, Crystal. Let's see. I thought she was here.
Yeah, sorry, I'm still working on it.
Okay, she's working on the graph, right? Okay, working. David Maes. She working on the graph. Okay, Robert Faust. Did you plot the graph? You're done. Okay, let me, don't go yet. Let me, we started at 12 noon, right? So 1 hour already. Daniel Frady, how are you doing there, Daniel?
I'm good, Professor.
Okay, so I'm assuming that you finish everything, Robert. Daniel, what do you mean I'm good? Did you plot the graph?
Yes,
Oh, you plot the graph. What about what you're doing right now?
I am finishing up my confidence level.
Ah, okay, CL, let's put CL right in here. Olivia, are you there, Olivia? You're done? Okay. So let me write that down here. Next time I go through you, then just wait a few minutes and then I'll get back to you all. Okay, check Lou. Okay, did you plot the graph? I'm done. Okay, what are you doing right now? Working on the rest. Okay, working on the rest. I'm gonna put here W for working. Amalia, Gail.
We finished the graph, Professor.
Okay, good. So we're doing something else now, right? Okay,
Yes.
Tiffany. Yeah, do you finish the graph? What are you doing right now? You're done? Okay. All right. Let me finish everybody here, and then I'm gonna write some things for you to keep in mind, and then I'll let you go. Okay, so hang in there for now. Anthony, did you plot the graph? Anthony? Does the graph work on the rest? Okay. W for working. Sha, are you done with the graph, Sha? Done with the graph, what you're doing right now? Working on the rest. Okay, good. Daniel Yang. Pastor, can you check my work? I'm done and have a okay, let me, okay, let's, yeah, before you go, make sure you do what Daniel did. Upload your spreadsheet and I'll take a look at it, okay? That's a good idea, Daniel. So Jacob, Ryan McNeil, right? Ryan Jacob McNeil. Are you there, Ryan? You're done too? Okay, so go ahead, upload your graph there. Upload one per group, right? That's better to upload one from Claire.
Hi, I'm having a hard time switching the axes for the
Axis?
graph. Yeah.
Okay, you don't need to switch the graphs. I see your group number 6. Okay.
Yeah, I don't have it up, but it just won't let me like switch the columns, I guess.
Well, it's like I said, there's no need to switch the axis because this guy will automatically be plotted in the y-axis, and this other one is going to be automatically plotted in the x-axis. Okay?
Oh, okay. I was trying to do M and L squared.
Yeah, no,
not MG.
No, it's MG. It's the tension, right?
Okay.
The tension that you want to do it. Okay, so problem resolved, right? Mystery resolved. Okay, so you're working on that, George. Are you there, George? I don't see George in the list anymore. Okay, I'm gonna put it, I'll put a star here and question mark. Jennifer Ramirez. You're done, okay. Okay, did you upload your graph there, Jennifer? Make sure you upload, if you're done again, make sure you upload your graph. Noah?
Finishing up my confidence level.
Okay, you're doing CL, okay. Natalie?
I'm doing the same. I just need my CL and I'm done.
Okay, CL. Next, Mengshu. Sig figs, okay. Nathan. Working on CL, that's good. Sarina. Okay, did you plot your graph? Okay, what are you doing right now? Sig figs, okay, good. Next, Alexis. CL, okay, good. Next, Darnice. Sig figs, that's good. Sig figs, sig figs. Okay, so let's see. Toby, are you there, Toby? Yeah, Toby just walked away, right? Oh, no. Yeah, walked away from his computer. Oh, so let's just document here in the lab notes. Okay. Ways. I'm just gonna make a quick, summary of what you saw in the video. Okay. Ways to get a wave in a string, right? You need a source of vibration. Need a source of vibration. Okay. So there are two sources of vibration that we use. There at the college, we have a tuning fork. At LA Harbor, I'm talking about at LA Harbor, where I teach connected to the power line with a frequency of approximately 60 hertz. Okay. The other way of doing that is to use a speaker. Connected to a function generator. This one is a nicer way of doing. Use a speaker connected to a function generator. Okay. And in this case, you can tune the frequency. Okay. Change the frequency. So you have to you have to be careful while you perform the experiment. Okay, you perform the experiment. You have to be careful about measuring the wavelengths of the wave at the position. Let's see, wavelength. How do we measure the wavelength of the wave? Measure the distance between nodes, right? If you're measuring from one node to the other one, that's one node that's next to the other one, the wavelength that you're measuring is half of the wavelength. So the actual wavelength has to be multiplied by 2. Okay. If you measure the distance between adjacent nodes, you must multiply this measurement by 2 to get the actual wavelengths. To be careful about. One way to do is to measure the distance between let's say adjacent nodes. Adjacent. If you measure the distance between, you must multiply this measurement by 2 to get the actual wavelengths. However, if you can measure the distance between every other node, not every mode of vibration, you can do that, right? then you get the actual wavelengths. Okay. And so on, right? You don't need to measure just the length of the wavelength. If you have that, you have three modes, three lobes of vibration, you can measure the distance between the extreme nodes and then make proper adjustments to get the wavelengths and so on. But with the mechanical vibrator, notice that you do not have an actual node at its position, although it can be close enough, right? And you saw that in the video. Sometimes the nodes are either before or after the vibrator. Why is that? That happens? It happens because the vibrator itself has an amplitude of vibration. Okay. Consequently, you cannot have a node there. Just keep that in mind. Some of the little things about this experiment. We are tempted, when we perform the experiment, we are tempted to think that there is a node there at the vibrator, but that there is no, you cannot, it doesn't have a node there at the very position of the vibrator. It's going to be either after it or just before. Okay. Don't forget, node is a position where the amplitude of the wave is zero, right? The position where the amplitude of the wave is zero. Okay, those are the notes that I want you to keep in mind. There might be a question about those experiments, and that if you understand that, you have shown to me that you somehow understood the experiment, right? Ideally, we should be doing that in the lab. Ideally, we should be doing the actual lab. So let's see. Now I'm gonna check your group one. Did you upload your lab? Your spreadsheet? Nolan, you did, right? Okay. I see one here. Is it you didn't upload yet, right? So whenever you upload it, let me know, group one. Okay, just upload one per group, okay? Next, group two. Did you upload your spreadsheet already, Harun?
Yeah.
Yeah. Okay, I'm gonna check quickly. Let's see. Scanning for viruses.
Professor, isn't that lab 3?
No, it's lab 4, right? Let's see. Let's take a look at this, the syllabus. Here you go. Lab 1 was the simple pendulum. Lab 2 was the physical pendulum. Let's see, lab 3 was on Thursday, right? We did lab 3 on Thursday, remember?
No, I'm saying like the spreadsheet that you downloaded, does it say lab 3 on it? I don't.
It said lab 6 there. See that? Unless I put, who is talking? Who is that? Is that Harun?
Yeah, this is how.
Okay, let me see. I remember uploading lab 6. Did you change?
Yeah, I
this?
changed it to 4. At least it should be 4.
Yeah. Oh, yeah. That should be 4. Yes, it should be 4. Yeah. Some confusion here. Lab 3 is what we did last time. That was wave 2, wave 1. That was the physical pendulum. That was the simple pendulum. So it should be lab 4. Okay.
Yeah.
Did you upload it already?
Yeah.
Okay, but why I don't see it here? Let me see what's going on.
Yeah, I don't know why it's not showing.
Did you? Yeah, maybe it's gonna take some time.
I think just check the one that says that you are the owner of it. Check that
Yeah,
one.
let me see. Let's see. Yeah. Huh. Yeah, he didn't rename it, right? Strange. Huh. Interesting. Yeah, he didn't rename it. Yeah, and I downloaded lab 3, right? That's what I did. Here you go. Yeah, okay, that's the one I'm supposed to download. Yeah, for some reason it didn't rename it. I don't know why. Here you go. I'm refreshing the screen here. Yeah, didn't rename it. Supposed to rename it, but let's download it. Open. Come on, man. Yeah, okay, yeah. So here you go. Here's the slope. You're getting, see, we got a very good result, right? 0.03%. Okay. Okay, I don't see. Okay, if you want to go, you can go. Okay, so again, we are changing the L prime, and then we are finding out what is the mass, right? The way I did at that time, I asked the student to start at ½ meter, increase by 25 centimeters. That's what I asked the student to do. So group 1, if you're done, you can leave. Okay, what about group 2, right? Group 2, not group 1. Group 2, you can, if you're done, you can leave. Okay, group 3. Let's take a look at group 3 here. Group 3, let's see. Group 3, did you upload? Are you done, group 3? Zachary, are you there? Don't go until
I haven't uploaded it yet.
You haven't? Okay.
I haven't uploaded it yet.
That's Zachary, right? What about
Yeah.
Crystal? Crystal? Okay, let's move to lab to group 4. Okay, that looks like group 3 still didn't get it. Group 4, did you upload your spreadsheet already?
Yeah, should be number 3. I have to clean it.
Which one?
Folder.
This
3.
one here or this one here?
3.
3? Okay, between Pat and Daniel. Is that Daniel
Yep.
Rosal?
Yes.
Okay, let's download it. Make sure you delete whatever.
Yes.
Not your. You don't want me to go Daniel and attendance. Daniel Frady, right?
Yes.
So let's see here. 1, 2, 3, 4, 5. Values. Okay. Did they use Daniel? The original had n equal to 2 here.
I just moved it for 1 decimal place. It had E to it, whatever.
You have n equal to 2, that the original document?
Yeah, I haven't changed the original document.
You didn't change. Okay. So it was 2. Okay, that's good.
Yeah. Okay.
Just 2. Okay, good. Good to know. And frequency, we did the measurement with the strobe, right? That's the mu. 2, 3. Okay, and then I got 3, 1. Okay, here you go. That's the slope. Pretty close, right? 4%. Okay, so group 4, if you're done, you can go. I don't see anything there. Doesn't mean there's no mistakes, okay? So make sure you review that before you turn in
No, thank you.
the final one. Group 5, some of you were done.
We uploaded it, Professor.
Okay, so let's go there to group 5. Oops. Group 5, this one. You want this one here, right, Tiffany? Go. Open. Okay, make sure you didn't move anything around, right, Tiffany? You didn't move any of the tables around, did you, Tiffany? Nothing. Okay, thank you. Wow, it's 4 meters long, huh? Okay, that's a very long. Yeah, okay, so 2 modes of vibration. Okay. Make sure you get the right sequence digits here, Tiffany. Okay. This one depends on those 2 measurements, so you have to write down the right sequence digits there, okay? Okay. MG 1, 2, 3, 4. Yeah. Okay, you have 5 sequence digits here, right? 1, 2, 3, 4, 5. So you're supposed to have 5 here as well. We have 6 instead, okay? Make sure you correct that. Here is the graph, 2.1, n is equal to 2. Yes, 2.1. Yeah, 8%, that's good. R squared is 0.95. Okay. I'm not sure if the CL is correct, but make sure you correct the things that I picked up here, okay? So let's go to the next group, attendance, group 6. George, are you there, George? Yeah, I don't see George in the list anymore. Okay, group 6, did you upload the spreadsheet? Daniel Yang, are you there? Daniel? Okay, do you upload the spreadsheet? Yes, yes for both. Let's see, group 6. L4. And there is Ryan and there is Daniel. Okay, either one. Let's get that Daniel. Again, when you this was just a rough draft, okay? Make sure that when you upload the spreadsheet, make sure you upload when you upload the final spreadsheet, make sure you delete the rest. Okay, so group 6. 1, 2, 3. MG versus L prime square. 1, 2, 3, 4, 5. Yeah, those are measurements too, right? Yeah, we can measure the wavelengths. See this. Yeah, let's see. Okay, that's good. This group did from 1 meter to almost 2 meters, right? 1.93, 1% difference. CL. Okay, CL. Okay, R squared 0.9985. That's good. Okay, so if you want to go, you can go group 6. Let's go for group 7. Group 7. Yeah, have a good day too. Let's see if group 7 has any spreadsheet there. 4. I don't see any spreadsheet of your group there. Group 7.
Sorry, there was one uploaded. I think maybe one of my group members deleted it, changed something real quick.
Okay, make sure, right? Okay, I see it. Yeah, make sure, right? Let's download it. I was looking at my name here on the wrong place. So group 7. 130, that's good. Well, whatever you did here, yeah, see, there's nothing here, right? So maybe let me refresh my screen here. Oh, because here at the top, yeah.
I need to re-upload it. That should be the right one.
Yeah, okay, that's at the top. Was looking in the wrong place. Don't forget, make sure you label it properly, please. Now let's go zoom out. Yeah, no $sign here, okay? You didn't get the right format. Make sure you put the proper format. You click on currency instead of number. Fix that, please. Okay, frequency, blah, blah, blah. Okay. Straight line, L's going from, yeah. See this group when they collected this data, they came up with very small variations on the length of the string, I wouldn't recommend if they perform the experiment like that. Recommend that they do that like from 1 meter to 2 meters and keep a larger difference in the lengths. 2.71, yeah, 2% difference. That's good. Okay. Okay, I do not know if those numbers are correct, but you'll find out when I correct the report. Okay, so group number 7. Okay, you can go and group 8. Let's see if group 8 has a spreadsheet there. Okay, group 8, I don't see your spreadsheet number 4 there. Let's see, let's go. Sarina, are you there? Okay, did you upload the spreadsheet there to the group folder? Just giving me when I tried, really? Okay, let me try Alexis. Alexis, did you finish, Alexis? Okay, thank you, Sarina. Let me try Alexis instead. Are you there, Alexis? I don't hear Alexis.
Sorry, I'm having connectivity issues. Can you hear me?
Yeah, I hear you. So did you upload your spreadsheet already?
No, I'll upload it shortly.
Okay, and what about Darnis? Darnis, right? Or Darnis? Are you there? Let me put that here, uploading, right? Uploading. Are still working? Okay, good. So let's go back to group number 1. Group number 1, did you upload their spreadsheet? Is Toby there? Toby, are you there? No?
Yeah, I'm here, Professor.
Okay. Did you plot your graphs?
I'm working on it right now.
Okay, Pedro just uploaded, right? Okay, group number 1. Group Nolan.
Yeah, that's the right one.
Yeah, which one should I open?
The one below the highlighted one.
This one here?
Yeah.
Okay. So let's this is L5. Why is L5? Let's see, download it. Let's see, L prime, okay. Changing. Yeah, don't forget the resolution is to millimeter, right? So here you gotta fix that, okay? Resolution up to a millimeter. The resolution is up to 100ths of a gram. Okay. Wow, 13% difference, huh? Well, it is whatever it is, right? Wavelengths, okay. So those are the things that I have seen. Okay, so anybody else? Group. Did I check your? Let's see, group 3, group 1, group 6, 5, 4, 2. Did I check your spreadsheet, group 3? $125. Let me download this one.
I'm having some trouble uploading it from my phone.
Really?
Yeah, it's kind of hard doing it over mobile. I might
Yeah.
have to just send it when I get home.
Who's that?
Zachary.
Zachary? Okay, well, make sure you have an actual computer, okay? Using a phone.
Yeah, I need to get a laptop.
It's not ideal. It's just full of
I
trouble.
agree.
Okay, so here you go. Group number 3. Yeah, you didn't do any second digits, right? If you let me see here. Let me see.
I'm having trouble importing the file from my phone.
Yeah, but what about the other students? What about the other students?
I'm not sure.
Yeah, Crystal and Dave. Are you there, Crystal and Dave? Dave. I'm gonna put here a question mark. Crystal and Dave. Okay. Now, group 8, how are you moving? How are you doing there, group 8? $139, 20 more minutes to go. So let's see. Alexis, are you there, Alexis? Let me check your spreadsheet. Yeah, I don't see the spreadsheet yet. Yeah, have a nice day, Jennifer. Okay, if you're done, yes. If you're done, Pedro, yes, you can leave. Leave only if you're done, okay? So you can practice those things before within this allotted time. Okay, let's see here. I'll give you a little bit more of time. Let me take a little break. I'll be back shortly, okay? Which group are you, Sha? 5. 5. Sha, this one here. Okay. Okay, mass and frequency. Yeah, you gotta check this one here, okay? The linear mass density. The linear mass density depends on those 2 parameters, so you gotta put the right number of second digits there. Okay, 1, 2, 3, 4, 5. Yeah, okay, that's the graph. Don't forget to optimize the space of the graph. Gotta cut it, start it at 0.4, right? And start this one in the vertical at 1.5. Too large of a blank space here. What's the percentage difference you have? 8.69. Okay, those are the things that you have to fix. Okay. Let me